There's something strange hiding in the universe. Something that defies logic, something that shouldn't exist yet does. Imagine looking at a galaxy, expecting to see one bright, powerful core in its center, because that's how galaxies work, right? But instead you see two massive, glowing centers, right next to each other. It's as if the galaxy has two hearts, two minds, two centers of gravity locked in an impossible dance. Scientists call them double-nucleus galaxies, and they are one of the strangest, most mysterious phenomena in the universe. Why do some galaxies have two nuclei? Is it a sign of a long-lost galactic collision? Are we looking at the early stages of a supermassive black hole merger? Or could it be something even weirder, something we haven't even imagined yet? Astronomers have been trying to solve this mystery for years, but the deeper they look, the stranger it gets. Because not only do some galaxies have two nuclei, but some seem to be hiding even more than that. To understand how bizarre this is, you have to know what a galaxy's nucleus actually is. At the center of most galaxies, there's a supermassive black hole, an unimaginably dense object with the mass of millions or even billions of stars. This black hole sits at the very core, acting like an anchor, holding the galaxy together with its immense gravity. Around this black hole, you often find an active galactic nucleus, a bright, glowing region powered by matter spiraling into the black hole. This is what gives galaxies like the Milky Way their structure. But in double-nucleus galaxies, something has disrupted this order. Instead of one central core, there are two, sitting near each other like rival kings fighting for control. One of the best examples of this is NGC 6240, a chaotic, irregular galaxy located about 400 million light-years away. When astronomers first looked at it, they knew something was off. Its shape was strange, distorted, like it had been stretched and pulled apart by some violent event. And when they examined its core, they found not one, but two supermassive black holes, separated by just a few thousand light-years. That might sound like a lot, but in galactic terms, that's incredibly close. These black holes aren't just sitting there, either. They're moving toward each other, slowly but surely, on a collision course that will eventually merge them into one. So what does this mean? How do galaxies end up with two nuclei? The most common explanation is that these are the remnants of galaxy mergers. When two galaxies collide, their central black holes don't immediately combine. Instead, they spiral around each other, caught in a gravitational tug-of-war. Over millions of years, they get closer and closer until they finally merge into a single, even more massive black hole. But while they're still in this process, they create a double nucleus, a rare and temporary state that we just happen to be catching in action. But here's where things get even weirder. Some double-nucleus galaxies don't seem to be in the middle of a merger at all. Their two nuclei are too far apart, or they don't behave like black holes should. Some appear to be clusters of stars, instead of black holes. Others show no signs of a past collision. This has led to some truly wild theories. Could some of these galaxies be housing unknown cosmic objects, something other than black holes? Could they be remnants of a past universe, or a sign that our understanding of galactic evolution is incomplete? And then there's the biggest question of all: what happens when these double nuclei finally merge? When two supermassive black holes collide, they release an unimaginable amount of energy. The explosion is so powerful that it can shake space-time itself, sending ripples across the universe in the form of gravitational waves. These collisions are some of the most violent events in existence, and yet, we've never actually seen one happen in real time. We know they must occur, because we've detected their aftermath. But if we could catch one in action, it would be one of the most groundbreaking discoveries in astronomy. And what if a galaxy had more than two nuclei? What if, instead of a simple merger, we found a chaotic system with 3 or even 4 supermassive black holes, all caught in a gravitational battle? Some astronomers believe that in rare cases, galaxies can merge not just once, but multiple times, creating a cosmic battlefield of colliding black holes. These systems could be even more extreme than anything we've ever imagined, places where space and time are so warped that the usual laws of physics start to break down. But double-nucleus galaxies don't just challenge our understanding of black holes. They also raise questions about the fate of our own galaxy. Because right now, the Milky Way is on a collision course with another massive galaxy, Andromeda. In about 4.5 billion years, these two galaxies will crash into each other, creating a brand new galaxy in the process. And when that happens, the supermassive black holes at the center of both galaxies will have to decide, do they merge quickly, or do they spend millions of years locked in a spiraling orbit, creating a double nucleus of their own? Some scientists believe that our future galaxy, sometimes called Milkomeda, could go through a phase where it has two active nuclei, just like NGC 6240. If that happens, it would be one of the most spectacular sights in the universe. Imagine looking up at the night sky and seeing not one, but two bright, glowing cores shining like twin beacons from the heart of our galaxy. And then, millions of years later, those two cores would collide, unleashing a burst of energy powerful enough to be felt across the cosmos. But here's the real mystery. How many of these double-nucleus galaxies are out there, right now, hidden in the vastness of space? The truth is, we've barely scratched the surface. The universe is too big, and our telescopes, even the most powerful ones, can only see so far. For every double-nucleus galaxy we've found, there could be thousands, even millions more, waiting to be discovered. Some could be in the early stages of a merger, while others might be hiding something even stranger, something we don't yet have the technology to detect. And then there's the possibility that we're completely wrong about what these double nuclei actually are. What if they aren't black holes at all? What if we've misinterpreted the data, and these galaxies are hiding something else? Some astronomers have even suggested that in rare cases, a double nucleus could be the result of an unknown cosmic phenomenon, one that doesn't fit into any existing category. Could there be exotic objects in space that mimic the behavior of a galactic nucleus but are something entirely different? Could we be looking at evidence of an undiscovered force in the universe, something that defies our current understanding of physics? One thing is certain, double-nucleus galaxies are one of the biggest cosmic mysteries we've ever encountered. They challenge our understanding of black holes, galaxy formation, and even the nature of space-time itself. And the more we study them, the more questions we find. As we dig deeper into the mystery of double-nucleus galaxies, the questions keep piling up. Why do some galaxies seem to merge faster than others? Why do some have two distinct cores, while others show signs of an even more complex structure? And what if these double nuclei aren't just the result of chance galactic collisions, but something more fundamental to the way the universe itself evolves? One of the strangest things about these galaxies is how rare they seem to be. In a universe filled with billions of galaxies, you'd think that we would have found more examples of this phenomenon. But the truth is, they are incredibly hard to detect. Most galaxies appear to have only a single, dominant nucleus, and if a second one does exist, it's often hidden behind clouds of dust and gas. Even in cases where we've spotted two, we can't always tell if they are both supermassive black holes or if one of them is something else entirely. Take NGC 7727, for example. This galaxy, located about 89 million light-years away, contains two supermassive black holes that are just 1,600 light-years apart, closer than almost any other pair we've observed. But what's strange about this galaxy is that the second black hole isn't as active as we'd expect. Normally, when black holes are in the process of merging, they generate enormous amounts of energy, lighting up the surrounding space as matter falls into them. But in this case, one of the black holes seems to be almost dormant, raising questions about how these systems evolve. Could it be that some black holes enter a quiet phase before merging? Or could it be a sign of a completely different process at work? Another strange case is Markarian 739, a galaxy that was found to have two active supermassive black holes, both emitting powerful jets of radiation. This discovery was significant because it suggested that double-nucleus galaxies could sometimes have two independently feeding black holes, rather than just a single, dominant one. If this is true, then it raises another question. Could there be galaxies out there with multiple active nuclei, each housing a black hole that is still growing? And if so, could these galaxies eventually turn into some of the brightest, most energetic objects in the universe? Some scientists have even speculated that double-nucleus galaxies might be the missing link in our understanding of quasars, supermassive black holes that shine so brightly they outshine entire galaxies. Quasars are thought to form when a black hole is consuming vast amounts of material, producing an intense glow that can be seen across billions of light-years. But what if some quasars are actually the result of two black holes merging? Could it be that double-nucleus galaxies are the early stages of quasar formation, and we're just catching them in a brief, transitional phase? And here's where things get even crazier. Some astronomers have proposed that in certain cases, double nuclei might not just be supermassive black holes orbiting each other, but something far more exotic. There's a theoretical idea called a wandering black hole, which suggests that some black holes can drift through galaxies, separate from the central core. These wandering black holes could be remnants of past galactic collisions, rogue objects that never fully settled into the nucleus. If this is true, then some double-nucleus galaxies might not be merging at all. They might just be home to a rogue black hole that is slowly making its way toward the center. Even more bizarre is the idea that some of these secondary nuclei might not be black holes at all. Some theories suggest that in rare cases, a second nucleus could actually be a dense cluster of stars, rather than a singular massive object. These star clusters could be relics of past galactic interactions, remnants of a smaller galaxy that got swallowed up but never fully merged. If that's the case, then studying these double nuclei could give us a glimpse into the history of galactic evolution, showing us how galaxies consume and absorb smaller ones over time. But here's the ultimate question: what happens when these double-nucleus galaxies finally merge? When two black holes collide, they produce one of the most violent and energetic events in the universe. The collision sends out gravitational waves, ripples in space-time that stretch and squeeze everything in their path. We've already detected these waves using instruments like LIGO and Virgo, proving that black hole mergers happen. But so far, all the mergers we've observed have been between much smaller black holes, nowhere near the size of the supermassive ones at the centers of galaxies. If we could catch a supermassive black hole merger in action, it would be one of the most important discoveries in modern astronomy. And there's a reason why scientists are so eager to find one. When two supermassive black holes collide, the final moments of the merger could reveal new physics, things we don't yet understand about how gravity works at extreme scales. Some theories suggest that these mergers could even warp space-time itself in ways we can't yet predict. There's even a small chance that they could create something called a naked singularity, a region where the laws of physics completely break down, exposing the very heart of a black hole for the first time. But there's a problem. The timescales involved in these mergers are enormous. Even when two black holes are just a few thousand light-years apart, it can take millions, or even billions, of years for them to finally collide. This means that most of the double-nucleus galaxies we see today won't merge in our lifetimes. But what if there's a way to speed up the process? Some scientists believe that certain cosmic events, like a passing star or another galaxy collision, could act as a trigger, accelerating the merger and making it happen much faster. If this is true, then there could be galaxies out there that are on the brink of merging right now, and we just haven't spotted them yet. And this brings us to another chilling possibility. If a double-nucleus galaxy does exist on the verge of a merger, and if we're close enough to it, the energy from that collision could have real effects on our own galaxy. Gravitational waves from such an event could subtly distort space-time, even here on Earth. And if the merger is close enough, it could even send out a burst of radiation powerful enough to affect planets. Some theories suggest that past galactic mergers could have triggered changes in Earth's history, maybe even influencing mass extinctions or other major cosmic events. So what does this all mean? Are double-nucleus galaxies just rare, fleeting occurrences, or are they a fundamental part of how the universe evolves? Could they be the missing piece in our understanding of black holes and galactic formation? Or are they pointing to something even deeper, some hidden force in the universe that we've yet to uncover? One thing is certain: we are only just beginning to understand these cosmic anomalies. With new telescopes like the James Webb Space Telescope and future gravitational wave detectors, We may soon have the ability to peer deeper into these galaxies, catching them in the act of merging. And when we do, we might just unlock some of the most profound secrets of the cosmos. Because the universe is full of mysteries, and double-nucleus galaxies are just one piece of a much bigger puzzle, one that could change everything we think we know about space, time, and the nature of reality itself. The deeper we dive into the enigma of double-nucleus galaxies, the more we begin to realize that they might be more than just rare cosmic anomalies. They could be windows into some of the most fundamental processes that shape the universe. But to truly grasp their significance, we need to explore what happens in the chaotic environments where these galaxies exist. Because if double-nucleus galaxies are part of a larger cosmic story, then understanding them might unlock answers to some of the biggest questions in astrophysics. One of the key aspects of these galaxies is the role of dark matter. Dark matter is the invisible substance that makes up most of the universe's mass, but we can't see it directly. Instead, we infer its existence by observing the way galaxies move. And here's where things get interesting. When astronomers study double-nucleus galaxies, they sometimes find that their motion doesn't make sense under normal gravitational laws. The two nuclei don't always orbit each other the way we'd expect, and sometimes they even appear to be moving in completely different directions. This has led to speculation that dark matter could be playing a role in shaping these galaxies. Could it be that some of these secondary nuclei are trapped in pockets of dark matter, altering their motion? Or could they be revealing something entirely new about the way dark matter interacts with normal matter? Even more puzzling is the fact that some double-nucleus galaxies seem to have active galactic nuclei, regions where supermassive black holes are feeding on matter and emitting intense radiation, while others appear strangely quiet. Normally, when galaxies collide, we expect to see a lot of activity, because the merging process stirs up gas and dust, feeding the black holes at the center. But in some cases, one nucleus is highly active while the other is completely dormant. Why? Could it be that some black holes go through phases of activity and inactivity? Or is there another mechanism at play that we don't yet understand? One theory suggests that the gas supply in these galaxies might be unevenly distributed. If one nucleus has access to more gas, it might become highly active while the other remains quiet. But another, more radical idea is that some of these secondary nuclei might not be traditional black holes at all. Instead, they could be something far stranger, like remnants of an ancient quasar that has since burned out. This would mean that some double-nucleus galaxies are not just merging galaxies, but fossil records of past cosmic events, preserving the history of long-dead quasars that once shined brightly across the universe. And speaking of quasars, there's another possibility that makes double-nucleus galaxies even more fascinating. Some researchers believe that the most powerful quasars we see today, those that emit more light than entire galaxies, could actually be the result of double-nucleus mergers. In other words, what we're witnessing when we look at a quasar might not be a single black hole devouring matter, but two black holes locked in a deadly spiral, getting closer and closer until they finally merge. If this is true, then studying double-nucleus galaxies might help us understand the origins of the most energetic objects in the universe. But here's where things get even more bizarre. There's a concept in astrophysics known as recoiling black holes. When two supermassive black holes merge, they don't always settle into a stable position in the center of the new galaxy. Instead, the energy released during the merger can actually kick the resulting black hole away, sending it hurtling through space at incredible speeds. This means that some double-nucleus galaxies might not even be in the process of merging at all. Instead, they could be evidence that one black hole is about to be ejected entirely, leaving behind a single nucleus. If this happens, where does the ejected black hole go? Some scientists believe that these runaway black holes could travel through intergalactic space, completely separated from any galaxy. In fact, there's a chance that some of these wandering black holes could be lurking much closer to us than we realize, invisible until they happen to pass through a region dense with gas and reignite as active quasars. Could it be that the universe is littered with these rogue black holes, each one a remnant of a past double-nucleus galaxy that didn't merge the way we expected? And if that's not strange enough, consider this. some double-nucleus galaxies appear to be surrounded by mysterious structures, long, stretched-out filaments of stars and gas that don't seem to match any known formation process. These structures, sometimes called tidal tails, are thought to be the remnants of previous galactic interactions, but they don't always behave the way we'd expect. In some cases, they appear to be stretching away from the secondary nucleus, almost as if something is pulling them apart. Could this be another sign of an unseen force at work, perhaps an interaction with dark matter, or even the effects of an unseen third nucleus hidden within the galaxy? And then there's the question of time. Because of the vast distances involved, when we look at double-nucleus galaxies, we're not seeing them as they are now, we're seeing them as they were millions or even billions of years ago. This means that some of the galaxies we observe today might have already merged, their two nuclei becoming one. But we won't know for sure until we develop better observational techniques. Future space telescopes, like the Nancy Grace Roman Space Telescope and the next generation of gravitational wave detectors, might finally give us the ability to see these mergers happening in real time, rather than just glimpsing their ancient past. And if we do, the implications could be staggering. If we can directly observe a supermassive black hole merger, we might finally get answers to some of the biggest questions in physics, like whether or not general relativity still holds at these extreme scales, or if new physics emerges in the most violent events in the cosmos. We might even uncover evidence of new forms of matter or energy that could completely change our understanding of the universe. But until then, double-nucleus galaxies remain one of the most tantalizing mysteries in astronomy. They challenge our understanding of how galaxies form, evolve, and interact. They raise questions about the nature of black holes, dark matter, and even the fabric of space-time itself. And perhaps most importantly, they remind us that for all we've learned about the universe, there is still so much we don't know. Because the cosmos is full of secrets, and every time we think we've uncovered one, another mystery appears just beyond our grasp. And that's what makes the search so thrilling. The deeper we investigate double-nucleus galaxies, the more we realize how much we don't understand. These galaxies defy expectations, challenging our current astrophysical models and leaving us with more questions than answers. And perhaps the biggest question of all is, what happens when these two nuclei finally merge? Does it always result in a larger, single supermassive black hole? Or is there a possibility that something even stranger is happening? One of the most fascinating aspects of galaxy mergers is the way they affect the surrounding space. When two galaxies collide, their individual black holes don't immediately merge. Instead, they enter a phase known as a binary black hole system, where the two supermassive black holes orbit each other at incredibly high speeds. This process can last millions of years, during which time the surrounding gas and dust are violently stirred up, creating bursts of star formation and intense radiation. But eventually these black holes will merge, and when they do, they release an enormous amount of energy in the form of gravitational waves. Gravitational waves are ripples in space-time, first predicted by Einstein over a century ago and finally detected by the LIGO Observatory in 2015. When two supermassive black holes collide, they send these waves rippling across the universe, carrying information about the event. But here's where things get really interesting. Scientists believe that the merging of two supermassive black holes in a double-nucleus galaxy could produce the strongest gravitational waves ever recorded. If we could detect such an event, it would allow us to study black hole physics in ways we never thought possible. But there's a problem. While we've detected gravitational waves from smaller black hole mergers, we have yet to directly observe a merger between two supermassive black holes. Why? One possibility is that these mergers take longer than we expect, meaning the galaxies we're observing today might still be in the process of merging for millions of years to come. Another possibility is that something is preventing these black holes from merging in the first place. Astrophysicists have proposed a concept known as the final parsec problem, which suggests that when two supermassive black holes get close to each other, they can become locked in an orbit that prevents them from merging. Instead of spiraling inward, they remain in a stable orbit for an indefinite period. If this is true, it could mean that some double-nucleus galaxies are stuck in a kind of cosmic limbo, where their black holes will never fully merge. But what if the final parsec problem isn't the only thing preventing these mergers? Some researchers believe that an unknown force, possibly related to dark matter or new physics beyond our current understanding, could be at play. If dark matter interacts with black holes in an unexpected way, it could create gravitational effects that alter the dynamics of these mergers. And if that's true, then double-nucleus galaxies might not just be oddities in space. They could be key to unlocking entirely new laws of physics. And then there's the possibility that some double-nucleus galaxies contain something even stranger than supermassive black holes. While most astronomers assume that these galaxies form when two black holes merge, there is another, more speculative idea. What if some of these secondary nuclei are not black holes at all, but something entirely different? Some scientists have suggested that these nuclei could be exotic objects like boson stars, hypothetical celestial bodies made entirely of dark matter. If such objects exist, they could revolutionize our understanding of both dark matter and the fundamental nature of gravity. But even if we assume that all double-nucleus galaxies contain black holes, there's still one final mystery to consider. What happens to the stars and planets that orbit these nuclei? In a normal galaxy, stars move in stable orbits around a single supermassive black hole. But in a double-nucleus system, the gravitational forces become chaotic and unpredictable. Some stars might be ejected from the galaxy entirely, flung into intergalactic space at speeds of millions of miles per hour. Others might be drawn into the black holes, triggering massive bursts of radiation known as tidal disruption events. And what about planets? Could there be planetary systems orbiting these binary black holes, experiencing extreme gravitational forces as they navigate between two competing centers of gravity? Some scientists believe it's possible, and if so, the conditions on such planets would be unlike anything we've ever imagined. Imagine a world where the sky is dominated by two giant, glowing nuclei, where the pull of gravity shifts unpredictably as the planet moves between them. Could life exist in such an environment? Could civilizations evolve in a galaxy where the very structure of space is constantly changing? These are the kinds of questions that make double-nucleus galaxies so fascinating. They force us to confront the limits of our knowledge and push us to think about the universe in new and unexpected ways. Because in the end, every discovery we make about these galaxies doesn't just teach us about them, it teaches us about the fundamental forces that govern the cosmos. And the more we study them, the more we realize just how much we still don't know. If double-nucleus galaxies hold the answers to some of the universe's biggest mysteries, then the biggest challenge we face is figuring out how to study them in greater detail. Right now, our most powerful telescopes, like the Hubble Space Telescope and the James Webb Space Telescope, have given us incredible images and data, but even these advanced observatories have limits. The problem with studying double-nucleus galaxies is that they are often located millions or even billions of light-years away, making them difficult to observe in high resolution. To truly understand what's happening inside these galaxies, scientists need to rely on indirect methods, analyzing the movement of stars, measuring the radiation coming from the nuclei, and using computer models to simulate what's happening. One of the most useful tools for this research is spectroscopy, which allows astronomers to break down the light coming from these galaxies and determine what elements are present, how fast objects are moving, and whether there are strong gravitational forces at play. Spectroscopy has already revealed some fascinating insights. For example, researchers have found that in many double-nucleus galaxies, one of the two nuclei is often more active than the other. This suggests that while one black hole is actively consuming matter and producing massive amounts of radiation, the other might be dormant, or in a quieter phase of its life cycle. But why does this happen? One possibility is that the two black holes are at different stages of their growth. Another possibility is that external factors, such as the amount of gas available, play a role in determining which black hole becomes dominant. But there's an even bigger challenge when it comes to observing these galaxies: dust. Many double-nucleus galaxies are surrounded by enormous amounts of cosmic dust, which can obscure the view of their central regions. This is especially true in galaxies that are in the early stages of merging, where the collision between the two systems creates massive clouds of debris. While infrared telescopes like James Webb can see through some of this dust, there are still limits to what we can detect. To get around this problem, scientists are turning to radio telescopes, which can detect signals that are not blocked by dust. Observatories like the Very Large Array, VLA, and the Atacama Large Millimeter/Submillimeter Array, ALMA, are being used to study the radio emissions coming from double-nucleus galaxies, providing new insights into their structures. One of the most exciting discoveries made with these telescopes is that some double-nucleus galaxies appear to have vast jets of energy shooting out from their centers, powerful streams of charged particles moving at nearly the speed of light. These jets are created when material falls into a black hole and is accelerated to extreme speeds before being ejected into space. In some cases, these jets extend for thousands of light years, shaping the structure of the entire galaxy. But here's where things get strange. In many double-nucleus galaxies, the two black holes don't always produce jets at the same time. Instead, one nucleus might have a powerful jet, while the other appears relatively inactive. This raises an interesting question. If both nuclei contain black holes, why don't they both produce jets? Some researchers believe that it has to do with the way black holes interact with their surroundings. If one black hole is absorbing more material than the other, it might generate a jet while the other remains quiet. But there's also another possibility, one that challenges our current understanding of black hole physics. What if these jets are interacting with each other in ways we don't fully understand? In a normal galaxy, a single supermassive black hole produces a jet that moves outward unimpeded. But in a double-nucleus galaxy, the second black hole could disrupt this process, altering the trajectory of the jet or even absorbing some of the material. Some computer simulations suggest that in certain conditions, the two black holes could create a kind of jet war, where their competing gravitational forces distort the streams of energy and create bizarre, looping patterns in space. If this is true, it could help explain some of the odd structures we've observed in double-nucleus galaxies. In some cases, astronomers have found galaxies where the jets appear twisted or misaligned, as if they'd been redirected by some unseen force. Could this be the result of two black holes battling for dominance? And if so, what does that tell us about the way black holes interact over time? These are questions that scientists are still trying to answer. But one thing is certain, studying double-nucleus galaxies isn't just about understanding individual galaxies. It's about unlocking the deepest secrets of black holes, gravity, and even the fundamental nature of space and time itself. And perhaps the most mind-blowing possibility is that some of these galaxies could be providing evidence for something even bigger, something that could change our entire understanding of the universe. Some researchers believe that double-nucleus galaxies might not just be formed by mergers of two galaxies. Instead, they could be the remnants of even larger cosmic events, collisions between entire clusters of galaxies. If this is the case, then studying these galaxies might give us insight into the largest structures in the universe and how they evolve over time. But there's another, even more radical idea. Some physicists have speculated that certain double-nucleus galaxies could be the result of interactions with parallel universes. According to some interpretations of quantum physics and string theory, our universe might not be the only one. Instead, it could be part of a vast multiverse, where different universes occasionally interact. If this is true, then double-nucleus galaxies could be signs of these interactions, places where the gravitational influence of another universe is bleeding into our own. While this idea is still highly speculative, it's not entirely impossible. Some cosmologists believe that if another universe were to interact with ours, one of the most noticeable effects would be strange gravitational distortions, exactly the kind of odd behavior we see in double-nucleus galaxies. Could it be that these galaxies are more than just cosmic collisions? Could they be glimpses into a deeper reality, one that we're only just beginning to understand? For now, we don't have the answers. But one thing is clear, double-nucleus galaxies are not just rare cosmic oddities. They are some of the most important objects in the universe, holding clues to the nature of black holes, the evolution of galaxies, and even the possibility of multiple dimensions. And the more we study them, the more we realize just how little we know. The mysteries surrounding double-nucleus galaxies continue to deepen as astronomers refine their observations and explore new theories. One of the biggest questions that remains unanswered is how common these galaxies actually are. Since they often appear in the aftermath of galaxy mergers, scientists originally thought they were rare, existing only in select cases where two supermassive black holes happen to be close enough to form a double nucleus. But as telescopes become more advanced and sensitive, researchers are discovering more of these galaxies than expected, suggesting that they might be far more common than we once believed. If double-nucleus galaxies are not as rare as previously thought, it raises a crucial question: why do they form so frequently? One possible explanation is that galactic mergers are simply far more common than we originally estimated. The universe is filled with billions of galaxies, and gravitational forces are constantly pulling them together, leading to collisions on massive scales. When two galaxies merge, their black holes don't immediately combine into one. Instead, they enter a chaotic phase where they orbit each other, creating a double nucleus. However, not all mergers result in a double nucleus galaxy. Some black holes merge relatively quickly, forming a single, larger black hole in the center of the newly combined galaxy. But in other cases, the process takes longer, leaving two distinct nuclei visible for millions of years. The reasons behind these differences remain one of the biggest mysteries in astrophysics. One factor that might influence whether a galaxy develops a double nucleus is the amount of gas and dust present during the merger. If the merging galaxies are rich in gas, the black holes might be surrounded by dense accretion disks, which could slow down their movement and prevent them from merging quickly. This could explain why some double-nucleus galaxies persist for millions or even billions of years without forming a single black hole. Another theory suggests that the angle of the collision plays a major role. If two galaxies merge head-on, their black holes may collide and combine relatively fast. But if the merger happens at an angle, the black holes could end up orbiting each other in a complex dance, remaining separate for long periods. This leads to another fascinating question: what happens when the two black holes in a double-nucleus galaxy finally merge? Scientists believe that when two supermassive black holes collide, they produce an enormous release of energy in the form of gravitational waves, ripples in spacetime that spread outward at the speed of light. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected the first-ever gravitational waves from a black hole merger, confirming a prediction made by Albert Einstein a century earlier. But those waves came from relatively small black holes, just a few times the mass of our Sun. A merger between the supermassive black holes in a double-nucleus galaxy would be millions or even billions of times more powerful, producing gravitational waves on a scale we've never seen before. Scientists are now working on projects like the Laser Interferometer Space Antenna, LISA, a space-based observatory that will be able to detect these massive gravitational waves. If we can observe the final moments of a black hole merger in a double-nucleus galaxy, it could give us an unprecedented view of how gravity behaves under the most extreme conditions in the universe. But here's where things get even stranger. Some theories suggest that when two black holes merge, they don't just create gravitational waves. They might also produce what's known as a recoil kick. This means that instead of simply merging and staying in place, the newly formed black hole could be violently ejected from the galaxy at incredible speeds. If this is true, it could mean that some double-nucleus galaxies don't actually have two black holes anymore. One of them may have already been flung out into intergalactic space. And if that's the case, there could be rogue supermassive black holes drifting through the universe, completely undetectable unless they happen to pass through a cloud of gas and start consuming matter again. This idea isn't just theoretical. Astronomers have already found evidence of galaxies that appear to be missing their central black holes, leading some to suspect that they were ejected after a merger. If this happens frequently in double-nucleus galaxies, it could mean that the universe is filled with wandering black holes, moving silently through the darkness, waiting for their next meal. But perhaps the biggest mystery of all is what double-nucleus galaxies can tell us about the ultimate fate of the universe. As we continue to study these galaxies, we might uncover deeper truths about how galaxies evolve over billions of years. Could it be that all galaxies eventually undergo mergers, forming larger and larger structures until only a few giant galaxies remain? Some cosmologists believe that this process, where smaller galaxies merge into bigger ones, is leading toward a future where only a handful of massive galaxies exist in the universe. If that's the case, then double-nucleus galaxies are not just cosmic anomalies. They are stepping stones in a much larger process that is reshaping the very structure of the cosmos. And this raises another profound question. If galaxy mergers continue indefinitely, could we eventually reach a point where all galaxies merge into one? Some theories suggest that in the far future, billions of years from now, the universe could become dominated by a single, ultra-massive galaxy, containing all the matter from every galaxy that has ever existed. But this idea is complicated by another mystery, the expansion of the universe. Right now, the universe is expanding at an accelerating rate due to a mysterious force known as dark energy. If this expansion continues, it could eventually pull galaxies away from each other so quickly that mergers become impossible, leaving double-nucleus galaxies as rare relics of a time when galaxies still collided frequently. Which fate is more likely? Will the universe continue merging galaxies together until only a few remain, or will expansion separate them forever? Double-nucleus galaxies might hold the key to answering this question, providing us with a glimpse into the future of the cosmos. No matter what the answer is, one thing is clear: the existence of double-nucleus galaxies is reshaping our understanding of the universe in ways we never expected. From black hole physics to cosmic evolution, from gravitational waves to the mysteries of dark energy, these galaxies are forcing us to rethink everything we thought we knew about space. And as our technology improves, allowing us to peer deeper into the cosmos than ever before, one thing is certain: we are only just beginning to unlock the secrets of double-nucleus galaxies. The more we learn, the more questions we uncover, and the more we realize just how much of the universe remains unknown. The study of double-nucleus galaxies is not just about understanding how galaxies evolve, it also provides an incredible opportunity to test the most fundamental theories of physics. At the heart of every double-nucleus galaxy is an unresolved battle between gravity, relativity, and quantum mechanics. Each of these forces plays a role in shaping the dynamics of these galactic cores, yet we still don't fully understand how they interact at the extreme scales of merging black holes. One of the biggest unanswered questions in physics is what happens at the event horizon of a black hole. According to general relativity, a black hole's event horizon is the ultimate boundary. Anything that crosses it is lost forever, crushed into the singularity at the center. But quantum mechanics suggests that information cannot be truly lost, leading to one of the greatest paradoxes in modern science: the black hole information paradox. Double-nucleus galaxies provide an opportunity to study this paradox in action. When two supermassive black holes spiral toward each other, and eventually merge, the energy released should carry information about their past states. But if black holes erase all information, as relativity suggests, then where does that information go? Some physicists believe that the merging process might produce a detectable echo of quantum information, revealing clues about what happens inside black holes. To detect these signals, astronomers are turning to gravitational wave observatories like LIGO and Virgo, as well as the upcoming LISA mission. By studying the ripples in space-time created by black hole mergers and double-nucleus galaxies, scientists hope to find subtle deviations from what classical physics predicts. These deviations could hint at a deeper, quantum-level theory of gravity, one that unites general relativity and quantum mechanics. But beyond the physics, double-nucleus galaxies also offer a window into the distant past. Since light takes time to travel, when we observe these galaxies, we are looking at them as they were millions or even billions of years ago. Some of these galaxies may hold clues about the earliest periods of the universe, when galaxies were first forming and supermassive black holes were beginning to grow. Some scientists believe that double-nucleus galaxies could even help us understand how the first black holes formed. In the early universe, small black holes could have merged repeatedly, forming the massive ones we see today. If double-nucleus galaxies are a snapshot of this process in action, they could reveal the missing link between the first stars and the giant galaxies we observe now. There is also the question of how these galaxies impact their surroundings. When two black holes orbit each other in a double nucleus, their intense gravitational forces can stir up gas and dust, triggering rapid bursts of star formation. Some of the brightest galaxies we see today may have been powered by the activity of merging black holes. But at the same time, these galaxies can also be destructive. The immense gravitational interactions can launch stars out of the galaxy at incredible speeds, creating what are known as hypervelocity stars. These stars move so fast that they escape their home galaxies entirely, traveling alone through intergalactic space. Even entire solar systems could be ejected in this process. Some astronomers speculate that there may be rogue planetary systems drifting through the void, torn from their galaxies by the chaos of double-nucleus interactions. If these planets exist, they would be among the loneliest objects in the universe, wandering through the darkness without a star to orbit. And then there's the question of what happens when these galaxies reach their final stage. Eventually, most double-nucleus galaxies will see their black holes merge into one. When this happens, the new, larger black hole might settle into the center of the galaxy, or, in some cases, it could be violently ejected. If a black hole is kicked out of its galaxy, it could leave behind an empty core where the nucleus used to be. These so-called naked galaxies would have no central black hole to anchor them, potentially leading to strange and unexpected consequences. Could such galaxies continue forming stars? Could they survive indefinitely, or would they slowly break apart? The study of double-nucleus galaxies is still in its early stages, and there is much we don't yet understand. But as technology advances, we are getting closer to answering some of the biggest questions about them. With new telescopes like the James Webb Space Telescope and upcoming gravitational wave detectors, we may soon be able to witness the final moments of these galactic collisions in real time. Each discovery brings new questions, and each answer leads to deeper mysteries. What we do know is that double-nucleus galaxies are not just rare cosmic oddities. They are key pieces in the puzzle of the universe. They hold the secrets to how galaxies form, how black holes grow, and perhaps even how the fundamental laws of physics operate at the most extreme scales. But despite all we have learned, we are still only scratching the surface. The universe is vast, and its mysteries are endless. Double-nucleus galaxies are just one small glimpse into the grand, unfathomable story of cosmic evolution. And as we continue to explore, one thing is certain: the deeper we look, the stranger and more fascinating the universe becomes. The deeper we investigate double-nucleus galaxies, the more perplexing they become. These galaxies are not just a spectacle of cosmic evolution. They are active laboratories where some of the most extreme forces in the universe collide. And as we continue to study them, we uncover even more bizarre and unexpected phenomena, some of which could challenge our very understanding of physics itself. One of the most striking mysteries surrounding these galaxies is the strange behavior of the supermassive black holes at their cores. When two black holes orbit each other in a double-nucleus galaxy, they don't just sit quietly in the center. Instead, their immense gravity distorts the very fabric of space-time around them, creating what scientists call a gravitational vortex. This effect can be so powerful that it warps the movement of nearby stars, causing them to spiral in unexpected ways or even be ejected entirely from the galaxy. But what's even stranger is that some double-nucleus galaxies seem to have black holes that are not where we expect them to be. In some cases, one of the black holes appears to be off-center, wandering through the galaxy instead of staying in the middle. This raises a huge question: can supermassive black holes actually escape from their galaxies? Astronomers have long suspected that black holes can receive what is known as a gravitational recoil. When two black holes merge, the energy released in the process is so intense that it can create an immense kick, launching the newly merged black hole away from its original location. In theory, if this kick is strong enough, it could send the black hole hurtling out of the galaxy entirely, leaving behind a galaxy with no central black hole at all. This idea is particularly intriguing because it could explain certain galaxies that appear to be missing their central black holes. There are some galaxies where, despite all expectations, no supermassive black hole has been found. Could these galaxies be the remnants of past double-nucleus systems where the black hole was ejected? And if so, where do these rogue black holes go? Some astronomers believe that these wandering black holes could be drifting through intergalactic space, completely detached from any galaxy. If true, this would mean there are potentially thousands, or even millions, of rogue supermassive black holes moving unseen through the void. Each of these objects would be millions of times more massive than our Sun, yet practically invisible, detectable only by the gravitational effects they have on the matter around them. Even more mind-boggling is the possibility that some of these rogue black holes could still be active. If a black hole manages to capture enough gas and dust while drifting through space, it could continue feeding, emitting powerful jets of radiation that could be detectable from Earth. This means there may be entire active galactic nuclei floating through space, completely detached from any galaxy, like cosmic ghosts, illuminating the darkness. But what if some double-nucleus galaxies don't result in the ejection of a black hole? Instead, what if their black holes merge in such a way that they create something even stranger? Some researchers believe that under the right conditions, merging black holes could form what is known as a supermassive boson star. A boson star is a theoretical object made of exotic particles called bosons, which behave very differently from ordinary matter. Unlike regular stars, which shine by fusing hydrogen into helium, a boson star would be held together purely by quantum effects. Some physicists speculate that if two supermassive black holes merge and somehow avoid collapsing into a single event horizon, they could instead form a giant, ultra-dense boson star, a new kind of cosmic object that has never been observed. If such an object exists, it could provide answers to some of the biggest mysteries in astrophysics. It could explain dark matter, the unseen substance that makes up most of the mass in the universe. Some theories suggest that dark matter could be made up of tiny, hypothetical particles called axions, which could clump together to form boson stars. If double-nucleus galaxies are producing these objects, they could be key to unlocking one of the greatest secrets of modern science. Another possibility is that some merging black holes could create wormholes, shortcuts through space-time that could, in theory, connect distant parts of the universe. If this is the case, double-nucleus galaxies could be more than just sites of violent black hole mergers. They could be gateways to entirely new regions of the cosmos. Of course, this remains speculative, but it raises an intriguing question. Could some double-nucleus galaxies be hiding something even stranger than black holes? Could they be harboring unknown types of cosmic objects, things we have never seen before? This idea might not be as far-fetched as it seems. Some double-nucleus galaxies exhibit unusual energy signatures that do not match the expected patterns of black hole mergers. In some cases, astronomers have detected bursts of radiation that seem to come from empty space, as if something invisible is releasing massive amounts of energy. Could this be evidence of exotic new physics at play? The deeper we dive into the mysteries of these galaxies, the more we realize how little we truly understand. Double-nucleus galaxies are not just rare cosmic oddities. They are proving grounds for the most extreme forces in the universe. They are places where time itself is distorted, where the laws of physics are stretched to their limits, and where the fate of entire galaxies is decided in cosmic battles between black holes. And yet, despite all the progress we've made, these galaxies still hold secrets that we have yet to uncover. What other strange objects could be lurking within them? What new physics might they reveal? The study of double-nucleus galaxies is far from over. In fact, it may only be just beginning. The deeper we look into double-nucleus galaxies, the more they defy expectations. These aren't just places where black holes merge, they're battlegrounds where the fabric of space-time itself is stretched and distorted in ways we can barely comprehend. Every new discovery about them seems to raise more questions than answers. What happens when two supermassive black holes finally collide? Could the process create an entirely new form of matter or energy? And could the extreme conditions in these galaxies reveal new laws of physics we haven't yet discovered? One of the strangest possibilities is that the merger of two supermassive black holes could result in something we don't yet have a name for, an object even more bizarre than a black hole, yet capable of holding immense amounts of mass without collapsing entirely. Some physicists theorize that these mergers could lead to the formation of ultra-dense gravastars, hypothetical objects that mimic black holes but lack a singularity at their core. Others speculate that the energy released could create massive distortions in space-time, potentially forming temporary wormholes or even gateways to unknown regions of the universe. But beyond theoretical physics, the impact of these mergers on the galaxies themselves is just as mind-blowing. As the black holes spiral closer and closer, their combined gravity warps the surrounding galaxy, sending out shockwaves that can trigger massive bursts of star formation. Entire clusters of stars may be born in the chaotic wake of these mergers, fueled by the redistribution of interstellar gas. At the same time, this turmoil can also rip apart existing structures, flinging stars out of the galaxy at mind-boggling speeds. These hypervelocity stars are among the fastest-moving objects in the universe, reaching speeds so high that they escape the gravitational pull of their home galaxy entirely. Some of these rogue stars may spend the rest of their existence wandering through the void of intergalactic space, forever cut off from any galaxy. In some cases, entire solar systems could be ejected in this process, meaning there might be planets out there, possibly even Earth-like ones, drifting alone in the darkness, without a star to orbit. This raises an even bigger question: could double-nucleus galaxies be responsible for spreading life throughout the universe? If a planet is thrown out of its galaxy but still harbors microbial life, it could theoretically carry that life across intergalactic distances. Some scientists have suggested that this could be one possible explanation for panspermia, the idea that life on Earth may have originated elsewhere in the cosmos. The chaotic nature of double-nucleus galaxies also has another fascinating consequence. It could be one of the main mechanisms driving galaxy evolution. When two galaxies merge, they don't just blend together smoothly. Instead, they undergo a long period of violent reshaping, with their structures twisting and distorting in response to gravitational interactions. During this process, their central black holes, if both galaxies had one, begin to orbit each other, creating a double nucleus. Over time, these black holes spiral inward and merge, reshaping the galaxy once again. But here's the strangest part. In some cases, the result of this process isn't a larger galaxy, it's a smaller one. Instead of simply combining, some galaxies appear to be stripped apart during these interactions, leaving behind only a dense, compact remnant. This has led astronomers to wonder whether some of the most unusual galaxies we see today, such as ultra-compact dwarf galaxies, could actually be the remnants of former double-nucleus galaxies that were torn apart by their own black holes. And then there's the issue of the missing matter. When astronomers study double-nucleus galaxies, they often find that something doesn't add up. The amount of visible matter, stars, gas, and dust, doesn't seem to be enough to explain the gravitational forces at play. This suggests that there may be enormous amounts of unseen matter in these galaxies, possibly in the form of dark matter. But what's even weirder is that in some cases, the dark matter appears to have been displaced, as if the chaotic motion of the black holes has somehow pushed it away. This could have profound implications for our understanding of dark matter. If double-nucleus galaxies can move or scatter dark matter, it might mean that this mysterious substance interacts with gravity in ways we don't yet understand. Some scientists even speculate that dark matter itself could play a role in forming double-nucleus galaxies, perhaps by acting as an invisible framework that guides the merging process. But no matter how much we learn, the mysteries keep piling up. Some double-nucleus galaxies have been observed emitting unusual signals, flashes of high-energy radiation that don't fit the expected pattern of black hole activity. In some cases, these signals seem to come from areas where there shouldn't be any significant energy sources at all. Could these be signs of unknown astrophysical processes, or even entirely new types of cosmic objects? There is also the eerie possibility that some of these galaxies might not be as dead as they seem. In many cases, the central activity in a double-nucleus galaxy slows down after the black holes merge, and the galaxy appears to enter a quiet phase. But recent observations have suggested that some of these galaxies can reignite millions or even billions of years later, suddenly erupting with activity again. This raises the question: what could possibly be reactivating these ancient galactic cores? One hypothesis is that dormant black holes in these galaxies can be woken up if they encounter a new source of fuel. If intergalactic gas or even an entirely new galaxy drifts too close, it could provide fresh material for the black hole to consume, causing it to flare back to life. This could mean that some double-nucleus galaxies might be in an endless cycle of dormancy and rebirth, flickering on and off like cosmic beacons over the course of billions of years. And then there's the possibility that we've only scratched the surface of what double-nucleus galaxies truly are. Could there be triple or even quadruple-nucleus galaxies out there, systems where multiple black holes are locked in a gravitational dance? So far, we've only found a handful of possible triple-nucleus galaxies, but given how rare even double-nucleus systems are, these could be even more difficult to detect. If they do exist, they could be among the most extreme environments in the universe, pushing the limits of what we know about black holes, gravity, and galaxy formation. Perhaps the biggest question of all is what role these galaxies play in the grand scheme of cosmic evolution. Are they just a temporary stage in the life cycle of galaxies? Or are they a fundamental part of how the universe itself is structured? Could understanding them help us unlock deeper truths about the forces that shape reality? One thing is certain: the more we learn, the more mysterious they become. Double-nucleus galaxies are not just cosmic collisions. They are windows into the most extreme and mind-bending aspects of the universe. They challenge everything we think we know about black holes, galaxy formation, and even the nature of space-time itself. And as we continue to build more advanced telescopes and detectors, we are bound to discover even more about these fascinating systems. Maybe we'll finally find the first confirmed case of a supermassive black hole being ejected from a galaxy. Maybe we'll detect an energy signature from a black hole merger that defies known physics. Or maybe, just maybe, we'll stumble upon something so unexpected that it forces us to rethink everything. The universe is vast, and its mysteries are endless. But double-nucleus galaxies stand out as some of the strangest, most complex, and most thought-provoking phenomena we've ever encountered. They remind us that no matter how much we learn, there will always be more waiting to be discovered. The deeper we dive into the nature of double-nucleus galaxies, the more it feels like we're peering into the very mechanisms that shape the universe. These galaxies aren't just places where black holes merge, they are cosmic laboratories where the most extreme gravitational forces warp time and space, and where new structures are forged in the aftermath of catastrophic events. But perhaps the strangest aspect of these galaxies is that we don't fully understand how common they are. Since the identification of some well-known double-nucleus galaxies, astronomers have debated whether they are relatively rare cosmic accidents, or if they represent a crucial phase in the life cycle of every major galaxy. The reason for this uncertainty is simple: we don't have the observational power to detect all of them. Many of these galaxies are hidden behind dense clouds of gas and dust, making it nearly impossible to observe their inner workings with traditional telescopes. However, the more advanced our technology becomes, the more we uncover hidden structures in the universe. Infrared and X-ray telescopes have allowed us to peer through the thick veils of gas that obscure galactic centers, revealing unexpected double nuclei in galaxies where we previously thought there was only one. Some of these discoveries suggest that double-nucleus galaxies might be far more common than we ever suspected, possibly even a normal stage in a galaxy's development. And this leads to an even more unsettling realization: if double-nucleus galaxies are part of an evolutionary cycle, then our own Milky Way may eventually become one. We already know that the Milky Way is on a collision course with the Andromeda Galaxy. The two galaxies are expected to merge in about 4.5 billion years, and when they do, their central black holes, one from each galaxy, will likely form a double nucleus. This means that our own galaxy will undergo the same kinds of extreme processes that we see in other double-nucleus galaxies, from gravitational disruptions to bursts of star formation. But this raises a disturbing question: what will happen to our solar system when this occurs? The collision of two galaxies doesn't mean that individual stars will physically crash into each other. Space is vast, and the distances between stars are immense. However, the gravitational turbulence caused by the merging process could drastically alter the paths of stars, planets, and other celestial objects. Some regions of the galaxy may experience intense compression, triggering new waves of star formation, while others may be flung outward, becoming part of intergalactic space. In other words, there is a real possibility that our solar system could be ejected from the Milky Way when this happens. If our Sun is caught in one of the chaotic gravitational interactions caused by the merging black holes, we could be hurled into deep space, drifting through the void without a galaxy to call home. This might sound terrifying, but it's important to remember that such an event would take billions of years to unfold. Humanity, if we still exist by then, will have had plenty of time to either prepare for it, or leave Earth entirely. But let's go beyond the fate of our solar system for a moment, and consider what these galactic mergers mean for the universe as a whole. The presence of double-nucleus galaxies suggests that galaxies are not static, unchanging structures. Instead, they are constantly evolving, merging, and reshaping themselves over cosmic timescales. This means that the universe we see today is not the same as it was billions of years ago, and it won't be the same billions of years from now. Some scientists believe that this process of galactic mergers and black hole interactions is one of the primary ways that the universe itself changes over time. As galaxies merge and their central black holes combine, the resulting energy release can influence the structure of the cosmos on a grand scale. Some theories even suggest that these mergers could be responsible for large-scale cosmic phenomena, such as the distribution of dark matter or the overall shape of the cosmic web, the vast network of galaxies and galaxy clusters that forms the large-scale structure of the universe. But there's another, even weirder possibility. What if double-nucleus galaxies hold the key to understanding the fate of the universe itself? Some cosmologists have proposed that the universe might be cyclical, going through endless cycles of expansion and contraction. If this is true, then galactic mergers and black hole collisions might be part of the mechanism that drives these cycles. Perhaps, over trillions of years, these processes contribute to the eventual collapse of the universe, triggering a new Big Bang and restarting the cycle all over again. While this idea remains speculative, it highlights just how much we still don't know about the fundamental nature of the cosmos. Double-nucleus galaxies challenge many of our assumptions about how galaxies evolve, how black holes behave, and even how gravity works in the most extreme conditions. They force us to confront questions that we may not yet have the tools to answer, questions that could redefine our understanding of the universe. But maybe the strangest question of all is this: if double-nucleus galaxies are so important to the evolution of the cosmos, could they also play a role in the development of life? We've already discussed the possibility that these galaxies could eject planets into intergalactic space, potentially spreading microbial life across the universe. But what if the energetic processes inside these galaxies also help create the conditions necessary for life to form in the first place? It's well known that supermassive black holes can influence star formation in their host galaxies. When a black hole consumes matter, it releases enormous amounts of energy in the form of radiation and high-speed jets of particles. This process can either suppress star formation, by blowing away the gas needed to form new stars, or it can trigger new bursts of star birth by compressing nearby gas clouds. If the latter is true, then double-nucleus galaxies, with their intensely active black holes, might actually be some of the most life-friendly places in the universe. Imagine a scenario where the chaotic interactions in a double-nucleus galaxy cause a surge in star formation, leading to the creation of billions of new stars and planetary systems. If just a fraction of these planets fall within habitable zones, then these galaxies could be responsible for producing an immense number of potentially life-bearing worlds. In this way, the destruction caused by merging galaxies could paradoxically be one of the driving forces behind the spread of life. And if life does exist in these galaxies, what would it be like? Would intelligent civilizations emerge in such a turbulent environment, or would the constant gravitational disruptions make it impossible for life to gain a foothold? If civilizations did arise, would they see the double nucleus of their galaxy as a mysterious force, something to be studied? And could some of them have developed the technology to harness the immense power of these black hole duos? These are questions that we may never be able to answer. But as our technology advances, we are getting closer to unlocking the secrets of these galaxies. Future telescopes like the James Webb Space Telescope and its successors will allow us to peer deeper into the universe than ever before, potentially revealing new double-nucleus galaxies that challenge our current understanding. We may even be able to directly observe the final moments of a black hole merger, capturing the exact moment when two singularities become one. Whatever we discover, one thing is certain: double-nucleus galaxies are among the most mysterious and mind-bending objects in the universe. They represent a crossroads of astrophysics, cosmology, and even the search for life itself. They are cosmic laboratories where the laws of physics are pushed to their limits, and where the universe reveals some of its most closely guarded secrets. And the more we learn about them, the more we realize that we are only scratching the surface. The universe is vast, and its mysteries are endless. But if double-nucleus galaxies have taught us anything, it's that the biggest discoveries often come from the most unexpected places. The concept of double-nucleus galaxies continues to raise profound questions about the nature of cosmic evolution, black holes, and the very structure of the universe itself. One of the most fascinating aspects of these galaxies is that they could be much more than just remnants of past mergers. They could actively shape the destiny of entire galactic clusters, influencing the way matter and energy distribute throughout the cosmos. To fully grasp the implications of double-nucleus galaxies, we need to examine the forces at play within them. The presence of two supermassive black holes in close proximity means that their gravitational fields are constantly interacting, creating a region of intense space-time distortion. These forces don't just affect the immediate surroundings of the black holes. They can extend for thousands of light years, pulling on stars, warping galactic arms, and even altering the trajectories of objects that stray too close. But what's even more incredible is that as these black holes move toward each other, they produce gravitational waves, ripples in spacetime that travel across the universe. These waves were first predicted by Albert Einstein over a century ago, but were only confirmed in 2015 when the LIGO Observatory detected them for the first time. The detection of gravitational waves has since opened up an entirely new way of studying the universe, allowing scientists to observe cosmic events that would otherwise be invisible. Now, imagine what happens when two supermassive black holes inside a double-nucleus galaxy finally merge. The energy released in this process is beyond comprehension. It's equivalent to converting multiple suns' worth of mass directly into energy, creating some of the most powerful gravitational waves the universe has ever seen. These waves ripple outward, shaking the very fabric of reality itself and carrying information about the final moments of the merger. But here's where things get even more bizarre. Some theories suggest that if a double-nucleus galaxy experiences a particularly violent black hole merger, the resulting gravitational waves could be so powerful that they physically kick the newly merged black hole out of the galaxy entirely. This process, known as a black hole recoil, means that the central black hole of a galaxy could be ejected into intergalactic space, leaving behind a galaxy with no central black hole at all. If this is true, then it means that some galaxies we see today might have once contained supermassive black holes, but lost them due to these powerful gravitational interactions. In other words, double-nucleus galaxies could be part of a much larger cosmic cycle where black holes are created, merged, and sometimes flung into the void, never to return. This idea challenges our understanding of how galaxies evolve and raises the possibility that there may be rogue supermassive black holes wandering through intergalactic space, untethered from any galaxy and moving at unimaginable speeds. But let's take a step back and ask an even deeper question. Could double-nucleus galaxies be a sign of something even more fundamental about the universe itself? The fact that these structures exist suggests that galaxies are not isolated, static entities. They are constantly interacting, colliding, and merging. This paints a picture of the universe as a vast, interconnected web where everything is in motion, and nothing remains the same for long. This idea aligns with some of the most cutting-edge theories in modern cosmology. For example, some scientists believe that the large-scale structure of the universe, the vast cosmic web of galaxies and dark matter, is shaped by the ongoing interactions between galaxies, with mergers and collisions playing a key role in determining how matter is distributed. In this sense, double-nucleus galaxies are not anomalies or rare occurrences. They are fundamental components of a constantly evolving universe. But could there be an even stranger connection between these galaxies and the nature of reality itself? Some physicists have proposed that the interactions between supermassive black holes and double-nucleus galaxies could provide insights into the nature of gravity, quantum mechanics, and even the possibility of extra dimensions. For instance, the way black holes behave during a merger could help us test theories of quantum gravity, one of the biggest unsolved mysteries in physics. If these theories are correct, then studying double-nucleus galaxies isn't just about understanding the evolution of galaxies. It's about unlocking the deepest secrets of the universe. They could be the key to answering questions about the nature of space-time, the origin of the cosmos, and whether our reality is part of a much larger, multidimensional structure that we have yet to fully comprehend. And here's where things take an even more mind-bending turn. What if double-nucleus galaxies aren't just cosmic laboratories for the laws of physics, but also potential cradles for exotic forms of life? We tend to think of habitable zones in terms of planetary systems, regions around stars where conditions might allow liquid water to exist. But what if entire galaxies have habitable zones? Some scientists have suggested that the extreme conditions in double-nucleus galaxies might actually be conducive to the formation of unique life forms. The intense radiation from two interacting black holes could provide the energy needed to drive complex chemistry in interstellar space, potentially giving rise to self-replicating molecules and environments we would never expect. If life can emerge in deep-sea hydrothermal vents on Earth, places that were once thought to be completely inhospitable, who's to say that something similar couldn't happen in the chaotic environment of a double-nucleus galaxy? Even more intriguing is the possibility that advanced civilizations, if they exist, might be drawn to these galaxies for scientific or technological reasons. A highly advanced civilization capable of interstellar travel would likely seek out the most extreme environments in the universe to test their theories and develop new technologies. Double-nucleus galaxies, with their immense energy output and exotic gravitational conditions, might be prime locations for such civilizations to establish research outposts, harvest energy, or even experiment with manipulating black holes themselves. Could it be that some of the anomalies we detect in double-nucleus galaxies, unexplained bursts of radiation, unusual gravitational distortions, or even irregular star formation patterns, are signs of advanced extraterrestrial activity? While there's no direct evidence for this yet, it's an idea that has been gaining traction in scientific circles. After all, if we were to become an interstellar civilization, wouldn't we seek out the most extreme and powerful places in the cosmos? But whether or not double-nucleus galaxies are home to extraterrestrial life, one thing is certain: they are among the most fascinating and mysterious structures in the universe. They challenge our understanding of gravity, cosmology, and galactic evolution, and they hint at a universe that is far more dynamic and interconnected than we ever imagined. And perhaps, as we continue to study these enigmatic galaxies, we'll find that they hold the answers to some of the biggest questions we've ever asked. Questions about the nature of time, the fate of the cosmos, and even the possibility of other intelligent beings out there among the stars. The more we learn, the more we realize how little we truly know. And in the end, that's what makes space mysteries like these so endlessly fascinating. The mysteries of double-nucleus galaxies don't just stop at their gravitational interactions or their role in shaping the universe. There's something even more mind-bending at play, something that might challenge our understanding of how galaxies form, evolve, and even how reality itself is structured. Let's talk about the idea that some double-nucleus galaxies might not be what they seem. Scientists have long debated whether all of these galaxies are the result of mergers between two separate galaxies or if some of them might have formed through an entirely different mechanism. There's a possibility that in some cases, what we're seeing isn't two separate galactic cores colliding but rather a single galaxy with a bizarre internal structure, one that defies conventional astrophysical models. Some theories suggest that certain double-nucleus galaxies could be the result of an unusual process where a supermassive black hole captures another smaller black hole from its surroundings and forces it into an orbit around itself. Instead of merging instantly, the two black holes could remain in a long-term dance, orbiting each other for millions of years while disturbing the surrounding stars and gas. This could create the illusion of a galaxy with two nuclei, even though it technically never experienced a full-scale merger. But what's even stranger is that some observations suggest that not all double-nucleus galaxies contain two black holes. In certain cases, one of the nuclei appears to be something else entirely, possibly a massive cluster of stars, a dense pocket of dark matter, or even a structure that we don't fully understand yet. This raises the possibility that some double-nucleus galaxies aren't actually the result of galaxy mergers but rather a new type of galactic formation that we haven't yet categorized. And here's where things get even more bizarre. Some astrophysicists have proposed that double-nucleus galaxies might be connected to an even deeper cosmic mystery, the nature of dark matter and dark energy. These two elusive components make up the vast majority of the universe's mass and energy, yet we can't see them directly. They influence galaxies in ways that we still don't fully understand, bending light, affecting rotation speeds, and even shaping the large-scale structure of the cosmos. Could it be that double-nucleus galaxies provide a window into the properties of dark matter? Some researchers have suggested that if dark matter interacts with itself in unusual ways, beyond just gravitational attraction, it could create dense pockets that mimic the behavior of a second galactic nucleus. This would mean that some of these galaxies might not have two physical cores at all but rather a single core surrounded by an unusual distribution of dark matter that gives the appearance of a secondary nucleus. This idea has profound implications. If true, it could mean that by studying double-nucleus galaxies, we might be able to gain direct insights into the nature of dark matter, something that has remained one of the biggest unsolved mysteries in physics for decades. If we can figure out why some of these galaxies appear to have a secondary core that doesn't behave like a normal black hole, we might be able to determine whether dark matter has properties that go beyond what we currently expect. And then there's the question of dark energy, the mysterious force that's causing the universe to expand at an accelerating rate. Some models suggest that dark energy might not be evenly distributed throughout the cosmos, but instead, it could concentrate in certain regions, influencing the motion of galaxies in unexpected ways. If this is the case, then double-nucleus galaxies might not just be gravitational oddities. They could be evidence of dark energy acting on a local scale, subtly altering the way galaxies behave. But what if we take this idea one step further? What if double-nucleus galaxies are actually connected in ways that go beyond traditional physics? Some fringe theories suggest that certain galactic structures, including double-nucleus galaxies, might be linked through cosmic strings, hypothetical, incredibly thin but massively dense structures that stretch across the universe and could act as pathways for energy and matter. If such strings exist, they could be influencing the way galaxies interact, possibly even explaining why some galaxies appear to have multiple nuclei instead of just one. This would mean that the universe isn't just a random collection of galaxies floating through space. It could be a vast, interconnected network where certain regions are linked in ways we've never considered before. Double-nucleus galaxies might be the cosmic equivalent of junction points, places where the structure of space-time itself behaves differently than anywhere else. And if that's true, it raises another question: could these galaxies be gateways to something even more mysterious? Some scientists have speculated that if cosmic strings or other exotic structures exist, they could theoretically be used as shortcuts through space-time, essentially acting as natural wormholes. If this idea holds any weight, then double-nucleus galaxies might not just be fascinating cosmic anomalies. They could be signposts for something much larger and more significant. What if these galaxies are part of a hidden cosmic network, where matter and energy can travel between distant parts of the universe in ways we don't yet understand? If an advanced civilization were to discover such a network, they might be able to harness it for intergalactic travel, using the gravitational and energetic properties of double-nucleus galaxies as stepping stones across the cosmos. Could it be that we're seeing signs of this in the strange behaviors observed in certain double-nucleus galaxies? There have been reports of unexpected bursts of radiation, irregular gravitational waves, and even anomalies in how stars move within these galaxies, things that don't quite fit with our current understanding of astrophysics. While these could simply be natural cosmic phenomena, it's hard not to wonder whether they hint at something more, a deeper cosmic structure that we're only beginning to perceive. As our telescopes and observational techniques improve, we may start uncovering even more strange properties of double-nucleus galaxies. The next generation of space observatories, like the James Webb Space Telescope and future gravitational wave detectors, could provide us with unprecedented insights into these galactic mysteries. We might finally be able to determine whether these galaxies are purely the result of mergers, or if something much more exotic is happening within them. And if we do find that double-nucleus galaxies hold the key to new physics, whether it's insights into dark matter, cosmic strings, or even wormholes, then the implications are staggering. It would mean that these galaxies aren't just interesting cosmic oddities. They could be some of the most important objects in the universe when it comes to understanding the fundamental nature of reality itself. Double-nucleus galaxies challenge everything we think we know about how the universe works. They force us to reconsider our models of galaxy formation, the behavior of black holes, and even the nature of space and time. They might be relics of past collisions, signs of hidden forces at play, or even cosmic waypoints that connect different parts of the universe in ways we can't yet imagine. One thing is certain: the more we study these galaxies, the more mysteries we uncover. And as long as those mysteries remain, we'll keep searching, questioning, and pushing the boundaries of what we know. Because in the vast, infinite universe, every mystery we solve only leads to even bigger questions. Questions that might one day reveal the true nature of existence itself. The more we unravel about double-nucleus galaxies, the more it becomes clear that these cosmic structures are not just rare occurrences. They might be crucial pieces in the puzzle of the universe itself. But what if they hold even greater secrets? Ones that challenge not just our understanding of physics but the very fabric of reality. One of the most fascinating possibilities is that double-nucleus galaxies might provide clues about higher dimensional space. In modern physics, particularly in string theory and M-theory, there's speculation that our universe isn't just the three-dimensional space we experience, plus time. It could be a vast, multidimensional reality where extra dimensions are hidden from our view. Could it be that what we're seeing in double-nucleus galaxies is evidence of higher dimensional interactions? Imagine for a moment that these galaxies aren't just what they appear to be in our three-dimensional universe. What if, in some way, they are interacting with or influenced by structures existing in a higher dimensional space? This could explain why some double-nucleus galaxies seem to defy traditional models of galaxy mergers and black hole interactions. If there are extra dimensions, matter and energy could behave in ways that seem strange from our limited perspective, potentially forming structures that appear to us as dual galactic cores, but which are actually projections of something much more complex. This idea isn't just science fiction. Some physicists have suggested that black holes themselves might be gateways to higher dimensions, or even that they could be connected in ways we don't yet understand. If double-nucleus galaxies contain two supermassive black holes in close proximity, could they be interacting through extra-dimensional forces? Could their gravitational fields be linked by structures beyond our comprehension, forming cosmic bridges that span across unseen dimensions? And if that's possible, what does it mean for our own galaxy? Could the Milky Way itself have hidden structures we haven't yet detected, structures that only become visible under certain conditions, just as we see in some double-nucleus galaxies? This could mean that the universe is far more interconnected than we realize, with unseen pathways and forces shaping its evolution in ways that we are only beginning to grasp. This leads us to another mind-bending possibility: the role of quantum mechanics in shaping these galaxies. In the quantum world, particles can exist in multiple states at once, and their behaviors can be influenced by phenomena like entanglement, where two particles remain connected no matter how far apart they are. Could it be that some double-nucleus galaxies exhibit quantum-like behaviors on a massive scale? Some scientists have proposed that at extreme cosmic scales, quantum effects might start playing a role in how galaxies form and evolve. If this is true, then what we're seeing in double-nucleus galaxies might not be the result of simple gravitational interactions, but something much stranger, perhaps an entangled relationship between two black holes, or even a superposition of galactic states where a single galaxy exists in two configurations at the same time. This might sound far-fetched, But consider that black holes themselves challenge our understanding of physics. Inside a black hole, the known laws of reality break down, creating a singularity, a point where space and time cease to behave normally. Now imagine what happens when two black holes exist in close proximity within a galaxy. Could they be distorting not just their surroundings, but the very nature of space and time itself? Could they be linked in ways that we don't yet understand, creating effects that ripple across the galaxy and beyond? Some researchers have even speculated that double-nucleus galaxies might be the best places to search for signs of exotic physics, things like microscopic wormholes, quantum fluctuations on a galactic scale, or even evidence of new fundamental forces that go beyond the four we currently know: gravity, electromagnetism, and the strong and weak nuclear forces. If such forces exist, they might be detectable in the way stars move within these galaxies, or in the strange bursts of energy that some of them emit. Speaking of energy, there's another mystery lurking in double-nucleus galaxies that scientists are still trying to solve: their unexpected levels of radiation. In many of these galaxies, we see intense emissions of X-rays, gamma rays, and other high-energy phenomena that don't fully match what we'd expect from normal galactic activity. Could this be a sign that something even more powerful is occurring within these galaxies? Something that hints at physics beyond our current understanding? One possible explanation is that these galaxies contain hidden quasars, massive, superheated regions around black holes that blast out enormous amounts of energy. But in some cases, the radiation coming from double-nucleus galaxies doesn't fit the typical quasar profile. Instead, it seems to fluctuate unpredictably or originate from places where we wouldn't normally expect such emissions. Could this be a sign that the second nucleus in some of these galaxies isn't just a black hole, but something else entirely? Some radical theories suggest that in certain cases, the second nucleus might not be a traditional black hole at all. Instead, it could be something far more exotic, perhaps a primordial black hole, formed in the early universe, which behaves differently from the ones we observe today. Or even stranger, some theorists have suggested that these galaxies could contain objects known as gravastars, hypothetical structures that mimic black holes but don't actually contain a singularity. If such objects exist, they could be among the most unusual and mysterious entities in the cosmos. But what if some double-nucleus galaxies are hiding something even weirder, something we've never seen before? Could they be the birthplace of new kinds of cosmic objects, ones that exist outside our current understanding of physics? There's even speculation that some double-nucleus galaxies might contain relics from a previous universe, structures that survived the Big Bang and carried over into our own. If this is true, studying these galaxies might not just teach us about the present universe, but also reveal secrets about what came before. And that brings us to the biggest question of all: what do double-nucleus galaxies mean for the future of the cosmos? Are they signs of how galaxies will continue to evolve, merging and reshaping themselves into entirely new forms? Or are they clues to something much deeper, something that hints at the true nature of space, time, and the forces that govern the universe? One thing is clear: double-nucleus galaxies are more than just cosmic oddities. They are windows into the deepest mysteries of existence, challenging everything we think we know about reality. As we continue to explore them, we may find answers that not only change our understanding of galaxies, but also reshape our view of the entire universe itself. The deeper we dive into the mystery of double-nucleus galaxies, the more we realize that they might not just be a cosmic anomaly but a fundamental aspect of how galaxies form, evolve, and interact with the universe on the largest scales. What if these galaxies are actually a crucial missing link in our understanding of how the universe operates? Could they be connected to some of the greatest unsolved mysteries in astrophysics, from dark matter and dark energy to the very nature of space-time itself? One of the most perplexing aspects of these galaxies is their potential link to dark matter. Dark matter is one of the biggest mysteries in physics, an invisible form of matter that doesn't emit, absorb, or reflect light, yet makes up about 85% of the total mass in the universe. Scientists only know it exists because of its gravitational effects on galaxies and galaxy clusters. But what if double-nucleus galaxies provide a unique way to study it? Consider this. If two supermassive black holes exist within a galaxy's core, their gravitational pull should influence the surrounding dark matter in strange ways. Some researchers believe that these galaxies might act as natural laboratories where dark matter interactions become more visible than in normal galaxies. If dark matter clumps differently in the presence of two galactic cores, this could provide critical insights into its properties. Does it behave like a particle, a wave, or something else entirely? Does it interact with itself in ways we haven't yet observed? Some scientists even speculate that the second nucleus in certain galaxies might not be a black hole at all, but instead a dense concentration of dark matter. This would mean that double-nucleus galaxies might not just be rare cosmic structures, but actually the first real evidence of dark matter behaving in unexpected ways. If this is the case, then understanding these galaxies could lead to one of the biggest breakthroughs in modern physics. And then there's the even bigger mystery of dark energy, the force that's causing the universe to expand at an accelerating rate. Unlike dark matter, which pulls things together through gravity, dark energy appears to be pushing galaxies apart, stretching the fabric of space itself. But how does this connect to double-nucleus galaxies? Some astronomers believe that these galaxies might be a sign of regions where dark energy and dark matter interact in unusual ways. If these forces are influencing each other within galaxies, it could mean that our entire understanding of cosmic expansion needs to be rethought. Perhaps these galaxies are places where dark energy's effects are weaker, stronger, or fundamentally different from what we expect. If we can pinpoint how the presence of two galactic cores affects the surrounding space, we might gain new insights into the mysterious force that's shaping the universe's future. And speaking of the future, what happens to these galaxies over billions of years? Do they always merge into a single structure, or is it possible that some of them remain in this dual state indefinitely? This is where things get even more fascinating because some theories suggest that double-nucleus galaxies might be an early stage of something much stranger, a new type of galactic formation that we've never seen before. What if some of these galaxies never fully merge, but instead reach a state of equilibrium where two black holes orbit each other indefinitely, creating a permanently dual core? If that's the case, then these galaxies might represent a previously unknown phase of cosmic evolution, one that could last for billions or even trillions of years. And if that's true, it could mean that double-nucleus galaxies are far more common than we currently realize, but we simply haven't developed the tools to detect them all yet. And then there's the mind-blowing possibility that these galaxies might not just be evolving, they might be gateways to something entirely new. Some physicists have speculated that certain regions of space, particularly near massive gravitational objects like black holes, could be connected to other parts of the universe in ways we don't yet understand. Could double-nucleus galaxies be places where space-time itself is behaving in an unusual way, perhaps bending, warping, or even creating connections to other regions of space? This brings us to one of the most extreme and controversial ideas in astrophysics: the possibility that some double-nucleus galaxies contain evidence of cosmic wormholes. A wormhole is a theoretical shortcut through space-time, allowing matter to travel vast distances instantaneously. If such structures exist, they would require enormous gravitational forces to remain stable, which is exactly what we see in double-nucleus galaxies. Could it be that some of these galaxies aren't just merging systems, but actually locations where space is folding in on itself, creating hidden tunnels that connect different parts of the universe? If so, they might be the best places to look for evidence of wormholes, places where gravity behaves strangely, where energy fluctuations don't match what we expect, or where stars and matter seem to be moving in ways that defy explanation. And if wormholes exist, what does that mean for the future of space travel? If humanity ever hopes to explore beyond our galaxy, we would need ways to cross the vast distances between stars without being limited by the speed of light. If double-nucleus galaxies provide real-world evidence that wormholes can exist, then they might also hold the key to intergalactic travel, an idea that has been purely theoretical until now. But here's the most unsettling thought of all: what if double-nucleus galaxies aren't just natural phenomena? What if, in some cases, the second nucleus isn't the result of a natural merger, but instead something artificial? If an advanced extraterrestrial civilization had the ability to manipulate galaxies on a cosmic scale, one of the most efficient ways to harness energy would be to position black holes in specific locations. Some theorists have even suggested that an ultra-advanced species could use supermassive black holes as power sources, or even as the foundation for creating stable wormholes. If that's the case, then could some of these double-nucleus galaxies be evidence of galactic-scale engineering? It's a wild idea, but not completely outside the realm of possibility. After all, we already speculate about megastructures like Dyson spheres, massive constructs built around stars to harness their energy. If a civilization were advanced enough, why wouldn't they attempt to manipulate galaxies themselves? So what does this all mean? Are double-nucleus galaxies just a fleeting stage of galactic evolution, or are they something far more profound, evidence of dark matter interactions, hidden wormholes, or even extraterrestrial engineering? One thing is certain: the more we study these galaxies, the more questions we uncover. In the coming years, as technology advances and telescopes become more powerful, we may finally start to get some answers. Perhaps we'll discover that these galaxies are far more common than we ever imagined, or maybe we'll find new physics hiding within their cores, physics that could change everything we think we know about the universe. Until then, double-nucleus galaxies remain one of the most perplexing and intriguing mysteries in astrophysics. They challenge our understanding of black holes, galaxy formation, dark matter, and even the fundamental nature of reality itself. And if history has taught us anything, it's that the biggest discoveries often come from the most unexpected places. So the next time you look up at the night sky, just remember, somewhere out there, among the billions of galaxies in the cosmos, are these strange, double-nucleus worlds, waiting for us to unlock their secrets. There's something eerie about the idea that galaxies could be hiding secrets within their very cores, secrets that challenge everything we know about space, time, and gravity. The more we look into double-nucleus galaxies, the clearer it becomes that they aren't just cosmic accidents. They could be evidence of unknown physics, strange gravitational interactions, or even something far beyond our understanding. One of the biggest questions scientists are trying to answer is how long these galaxies can maintain their double-nucleus state. In most cases, we assume that the two supermassive black holes at the center of these galaxies are in the process of merging. But what if that's not always true? Some studies suggest that certain double-nucleus galaxies might be stuck in an eternal dance, never fully combining into a single core. If that's the case, it raises a massive question: what's stopping them from merging? One possibility is that the galaxies have an incredibly delicate gravitational balance, where the forces between the two black holes and the surrounding stars are keeping them apart. Another possibility is that something unknown, perhaps a new form of matter or energy, is interfering with the merger process. If this is true, double-nucleus galaxies could be telling us that there are forces at play in the universe that we haven't even begun to understand. Another mind-bending possibility is that some of these galaxies are evidence of failed mergers. In most cases, when two galaxies collide, their central black holes eventually spiral toward each other and merge into a single, even larger black hole. But what if some collisions don't go as planned? There could be cases where two black holes get close but never actually merge, instead staying locked in an orbit that lasts for billions of years. This could create bizarre effects on the galaxies themselves. If two supermassive black holes are orbiting each other at high speeds, they could be flinging stars, gas, and dust in all directions. Some objects might get ejected entirely, thrown out of the galaxy at incredible speeds, possibly even becoming rogue stars that drift through intergalactic space. Others might be trapped in strange, elongated orbits that don't follow the usual patterns of galaxy rotation. And then there's an even wilder theory. What if some double-nucleus galaxies are actually signs of multiple universes colliding? It sounds like science fiction, but some physicists believe that our universe might not be the only one. If we live in a multiverse, then there could be other universes out there, each with their own laws of physics. Some theories suggest that when universes interact, they could leave behind strange cosmic signatures, one of which might be unexpected gravitational effects within galaxies. Could it be that some double-nucleus galaxies are places where two universes have briefly touched? If so, this could mean that we are looking at physical evidence of a multiverse, something that scientists have long theorized but never been able to prove. This could explain why some of these galaxies don't behave the way we expect them to. Maybe the second nucleus isn't just another black hole but instead a remnant of another universe, bleeding into our own in ways we can't yet comprehend. And here's something even more unsettling. What if double-nucleus galaxies are actually signals? We assume that these galaxies are natural formations, the result of mergers and gravitational interactions. But what if that assumption is wrong? Some researchers have speculated that highly advanced civilizations might use cosmic-scale engineering to manipulate entire galaxies. If a civilization had technology far beyond our own, it could theoretically move black holes, rearrange star systems, and even alter the structure of a galaxy itself. If that's true, then double-nucleus galaxies could be the result of something intentional rather than accidental. Perhaps an alien species has figured out how to harness the energy of black holes and is using them for purposes we can't even begin to imagine. Could these galaxies be artificial structures, built for unknown reasons? Are they part of some vast intergalactic experiment? Could they be cosmic beacons, sending signals across space in ways we don't yet understand? The idea of an alien civilization capable of manipulating entire galaxies might sound like pure speculation, but consider this. If intelligent life exists elsewhere in the universe, and if it has had billions of years to evolve, then it's entirely possible that some civilizations have reached a level of technological advancement that makes our own seem primitive. We tend to assume that extraterrestrial life, if it exists, would be using technology similar to our own. But what if that's not the case? What if some civilizations have advanced so far beyond us that their technology looks like natural cosmic phenomena? If that's true, then double-nucleus galaxies might not be random mergers. They might be evidence of intelligence on a scale we've never imagined. And if that's the case, what does it mean for us? Are we alone in the universe, or are we surrounded by civilizations so advanced that we can't even recognize their presence? Could some of these galaxies be artificial structures that are billions of years old, created by beings who have long since disappeared? Or are they still out there, watching, waiting, or perhaps even communicating in ways we haven't yet discovered? One thing is certain: the more we study double-nucleus galaxies, the more questions we uncover. Whether they are the result of natural cosmic evolution, strange gravitational effects, or something far more mysterious, they remain one of the greatest puzzles in astrophysics. As new telescopes and observatories come online, we may finally start to get some answers. Perhaps future missions will reveal evidence of hidden forces, unknown physics, or even the first real proof of extraterrestrial intelligence. Or maybe these galaxies will continue to defy explanation, remaining one of the universe's greatest and most enduring mysteries. But until we find those answers, one fact remains: somewhere out there, among the billions of galaxies in the universe, these strange, double-nucleus worlds continue to exist, waiting for us to unlock their secrets. The idea that double-nucleus galaxies might be more than just random cosmic mergers leads to an even deeper question. Could these structures be windows into the past, revealing the early formation of supermassive black holes? One of the biggest mysteries in astrophysics is how these colossal objects came to exist in the first place. We know that supermassive black holes sit at the centers of most large galaxies, but how did they get there? Were they born massive? Or did they grow over billions of years? If double-nucleus galaxies are systems where two black holes are still in the process of merging, then studying them might give us a glimpse into a time before our own galaxy had a single dominant core. This could mean that the Milky Way itself might have once been a double-nucleus galaxy, with two competing black holes before one eventually merged into the other. Could it be that some double-nucleus galaxies are snapshots of what all galaxies once looked like in their early stages? If that's the case, then we might be able to use them to study the very foundation of galactic evolution. The interactions between two black holes in close proximity could tell us about the forces that shape galaxies over billions of years. If we can measure how fast these black holes are moving, how much mass they are pulling in, and how they distort the space around them, we might finally get answers to some of the biggest questions about the history of the universe. And then there's the issue of the gravitational waves these galaxies might be producing. When two black holes orbit each other closely, they create ripples in spacetime, disturbances known as gravitational waves. These waves travel across the universe at the speed of light, carrying information about the objects that created them. Scientists have already detected gravitational waves from black hole mergers, but what if some double-nucleus galaxies are producing a steady stream of these waves as their black holes continue their cosmic dance? If that's true, then double-nucleus galaxies might be some of the strongest sources of gravitational waves in the universe. By studying them, we could learn about the invisible forces at work in deep space, uncovering details about the nature of black holes, dark matter, and possibly even new physics beyond Einstein's theories. Could it be that these galaxies are helping us map out an unseen side of the cosmos, one that can only be detected through distortions in spacetime itself? But here's where things get even stranger. Some double-nucleus galaxies don't just have two black holes. In rare cases, astronomers have found evidence of galaxies that seem to have 3 or even 4 central black holes. This raises an entirely new set of questions. How do multiple black holes interact with each other? Do they eventually merge into a single giant black hole, or do they remain in a complex orbital pattern indefinitely? If 3 or more black holes are present in a galaxy's core, the gravitational interactions between them could create extreme distortions in space and time. Some scientists believe that these chaotic systems might be launching entire stars and planets out of the galaxy at mind-boggling speeds. These hypervelocity stars have been observed before, lone stars traveling so fast that they are escaping the pull of their home galaxy and heading into intergalactic space. Could some of these runaway stars be the result of black holes flinging them out of double-nucleus galaxies? And if that's possible, then what happens if a planet gets caught in the middle of this chaos? Imagine a civilization on a distant world, living in a galaxy where 2 or more black holes are locked in a violent gravitational struggle. If their planet was flung out of its home system, it would become a rogue planet, drifting through the dark void between galaxies, completely cut off from any source of warmth or energy. Could there be entire civilizations trapped on planets that were thrown into intergalactic exile because of a double-nucleus galaxy? And that leads to another mind-bending possibility. What if some of these galaxies are hiding something even more extreme? If black holes are capable of warping space and time, could some double-nucleus galaxies be places where the laws of physics themselves start to break down? There are theories that suggest black holes might be linked to wormholes, hypothetical shortcuts through spacetime. If that's true, then double-nucleus galaxies could be the best places to look for evidence of these cosmic tunnels. Could it be that some of these galaxies contain gateways to other parts of the universe, or even to parallel realities? If an advanced civilization had figured out how to manipulate black holes, they might be using double-nucleus galaxies as intergalactic travel hubs. Could the strange, unexplained features of these galaxies be signs of artificial wormholes, built by civilizations far older and more advanced than we can imagine? And if that's the case, then what would that mean for us? Could it be that one day, humanity will uncover the true nature of double-nucleus galaxies and realize that they were never just random cosmic events? What if they are beacons, lighthouses in the cosmic ocean, signaling the presence of something, or someone, far beyond our current understanding? One thing is for sure. Double-nucleus galaxies remain one of the greatest mysteries of the universe. They challenge our understanding of physics, galactic evolution, and even the nature of space and time itself. The more we study them, the more questions we find. Are they the result of natural processes, or are they evidence of something far more profound? Could they be the keys to unlocking the deepest secrets of the cosmos? As we continue to explore the universe, new telescopes and future missions might finally bring us closer to answers. But until then, these strange galaxies remain an enigma, silently drifting through the vastness of space, holding secrets that could change everything we think we know about the universe. The implications of double-nucleus galaxies stretch far beyond just understanding how black holes merge. These galaxies could be testing grounds for some of the most extreme physics we can imagine. If 2 black holes in a double-nucleus system are actively merging, then their gravitational fields would be in constant turmoil, warping space and time in ways that challenge even our best models. But what happens if these black holes don't merge cleanly? What if their collision leads to a completely different outcome, something we haven't even theorized yet? One of the most mind-boggling ideas is that some double-nucleus galaxies could be sites where black holes don't just merge, but instead form something new, something beyond our understanding of physics. There are theories suggesting that if two supermassive black holes collide under just the right conditions, they might create a phenomenon known as a naked singularity. This is a point in space where gravity is so strong that it breaks all known laws of physics. But unlike a black hole, it doesn't have an event horizon to hide what's inside. If naked singularities exist, they could be the most extreme objects in the universe, exposing the true nature of reality in ways we can't even begin to comprehend. Could double-nucleus galaxies be home to such phenomena? If so, they might be the best places to test the limits of our understanding of gravity and space-time. But here's where things take an even weirder turn. If naked singularities exist in some double-nucleus galaxies, could they be leaking information from another universe? This idea comes from quantum mechanics and something called the information paradox. According to our current understanding, black holes shouldn't be able to destroy information. But if two black holes merge and form something new, then the question arises: what happens to all the matter, energy, and information that was inside them? If a naked singularity forms, could it act as a cosmic loophole, allowing information from another reality to bleed into our own? And if that's possible, then could double-nucleus galaxies be the locations of interdimensional events? Could they be points in the universe where strange anomalies occur, where reality itself bends in unpredictable ways? This might sound like science fiction, but the truth is, we don't know what happens when two massive black holes collide in the most extreme conditions. Some physicists believe these events could generate exotic forms of matter that don't exist anywhere else in the universe, or even open up brief windows into higher dimensions. If this is true, then double-nucleus galaxies might not just be places where black holes are merging. They could be places where the fundamental structure of the universe is being rewritten. Could it be that these galaxies are rare glimpses into a deeper layer of reality, one that operates on entirely different rules than what we know? And if so, is there a way to study them in more detail? This is where the future of astronomy comes into play. Scientists are developing telescopes that will be able to peer deeper into space and capture more details than ever before. The James Webb Space Telescope is already giving us unprecedented views of the cosmos, but even more advanced observatories are on the way. The upcoming Laser Interferometer Space Antenna, LISA, is designed to detect gravitational waves from merging black holes with incredible precision. If double-nucleus galaxies are indeed sending out powerful ripples in space-time, LISA might be able to capture them, allowing us to study these mysterious systems in a completely new way. But there's another question we have to ask. If double-nucleus galaxies are sending out gravitational waves, is it possible that they are also producing signals that we haven't even detected yet? Could these galaxies be emitting exotic forms of radiation, or even unknown particles that defy our current understanding of physics? If so, they could hold the key to discovering new forces of nature, forces that might explain the deepest mysteries of the universe, including dark matter and dark energy. Dark matter is one of the biggest mysteries in astrophysics. We know it exists because of the way galaxies move, but we still don't know what it is. Some theories suggest that dark matter might interact with black holes in ways we haven't yet detected. If that's the case, then double-nucleus galaxies, with their extreme gravitational environments, might be some of the best places to look for signs of dark matter. Could these galaxies be acting as natural laboratories, revealing the properties of a hidden substance that makes up most of the universe? And then there's dark energy, the mysterious force that's causing the universe to expand at an accelerating rate. If dark energy has any connection to gravity, then double-nucleus galaxies could be important clues in solving this puzzle. If the movement of their black holes is influenced by something beyond just regular gravity, then we might be able to detect traces of dark energy at work. But what if double-nucleus galaxies are even more than that? What if they are cosmic anomalies that don't just affect their own galaxies, but actually influence the universe on a much larger scale? Could it be that these rare galaxies play a role in shaping the structure of the cosmos itself? Some theories suggest that the distribution of galaxies in the universe isn't entirely random, that there are hidden patterns guiding the formation of large-scale cosmic structures. Could double-nucleus galaxies be signs of these hidden forces at work? And if they are, then what does that mean for us? Could it be that double-nucleus galaxies hold the answers to questions we haven't even thought to ask yet? Could they be the missing pieces in the puzzle of the universe, clues that, when finally understood, will reveal the true nature of reality itself? The more we study these galaxies, the more mysterious they become. They challenge everything we think we know about black holes, gravity, and the evolution of galaxies. But perhaps their biggest mystery isn't just about science, it's about what they mean for the future of humanity. If double-nucleus galaxies are windows into the most extreme forces in the universe, then could understanding them help us unlock new technologies, new forms of space travel, or even new ways of interacting with reality itself? As we continue to explore the cosmos, these strange galaxies remain some of the most intriguing objects out there. Whether they are signs of ancient collisions, glimpses into higher dimensions, or something even more mind-bending, one thing is certain: we have only just begun to scratch the surface of their secrets. And with each new discovery, we are reminded that the universe is far more complex, far more mysterious, and far more incredible than we ever imagined. The mysteries surrounding double-nucleus galaxies push us to the very edge of our understanding, forcing us to question not just what we know about space, but what we know about the fundamental nature of reality itself. These galaxies are more than just cosmic anomalies. They are potential gateways to new physics, new insights, and perhaps even answers to some of the biggest questions humanity has ever asked. One of the most fascinating aspects of these galaxies is the possibility that their dual nuclei could be relics of past galactic collisions. When two galaxies merge, their central black holes are drawn toward each other by gravity, eventually forming a binary system. Over millions of years, these black holes will spiral inward, emitting vast amounts of energy in the form of gravitational waves before merging into a single, even more massive black hole. But what if this process doesn't always go as expected? What if something interrupts the merger, leaving behind two distinct nuclei instead of just one? Some astrophysicists believe that certain conditions can prevent black holes from merging in a straightforward manner. For example, if a third black hole enters the equation, perhaps from another galaxy passing nearby, it could disrupt the merger, leaving the two original black holes locked in an eternal gravitational dance. This could explain why some double-nucleus galaxies appear to have two separate cores even though they should have merged long ago. But even more intriguing is the idea that some double-nucleus galaxies might not be remnants of past mergers at all. Instead, they could represent a completely different class of galaxy, one where dual nuclei are a permanent feature rather than a temporary stage in an ongoing collision. If this is true, it could mean that the formation of galaxies is more diverse than we ever imagined, with some galaxies evolving in ways that defy our standard models of cosmic development. This brings us to another strange question: what if some double-nucleus galaxies contain not just two black holes, but something entirely different? Could these galaxies harbor exotic objects that don't fit into our current understanding of astrophysics? There have been theories suggesting that extremely dense regions of space could create quasi-black holes, objects that have many of the properties of black holes but behave differently under extreme conditions. If such objects exist, then double-nucleus galaxies could be some of the best places to find them. And then there's the question of time itself. When we observe double-nucleus galaxies, we're not just looking at cosmic structures, we're looking back in time. Light from these galaxies has taken millions, sometimes billions, of years to reach us. This means that when we see a double-nucleus galaxy today, we're seeing it as it was eons ago. Could it be that some of these galaxies have already merged, and we just haven't seen it happen yet because of the vast distances involved? This raises the possibility that some of the most interesting events in the universe, massive black hole mergers, gravitational anomalies, and even potential cosmic-scale explosions, are already happening right now, but we won't witness them for millions of years. In other words, the true nature of double-nucleus galaxies might still be unfolding, and we're only seeing a snapshot of their evolution. But what about the regions surrounding these galaxies? If double-nucleus galaxies are sites of intense gravitational interactions, then they should also be places where some of the most powerful energetic events in the universe occur. We know that black holes at the centers of galaxies can create enormous jets of radiation, shooting out energy at nearly the speed of light. If a galaxy has two active black holes instead of one, then could it also have two of these jets? Some observations suggest that double-nucleus galaxies may be home to complex, high-energy environments where matter is being accelerated to near-light speeds in ways we don't fully understand. These jets could have massive effects on their surroundings, potentially influencing the formation of new stars or even reshaping entire regions of space. But if these galaxies are so extreme, could they also be places where we might find the answer to another great cosmic mystery? Where does all the missing antimatter in the universe go? When the universe was born, there should have been equal amounts of matter and antimatter. Yet today, almost everything we see is made of matter, with antimatter being extremely rare. Could double-nucleus galaxies hold clues to this mystery? Some physicists believe that powerful gravitational environments, like those found in double-nucleus galaxies, could create conditions where antimatter is more likely to form or survive. If this is true, then studying these galaxies might give us a new understanding of why our universe ended up dominated by matter instead of being a perfect balance of both. And if antimatter is more common in these galaxies, could that mean there are entire regions of the universe where antimatter galaxies exist? Could there be galaxies out there made almost entirely of antimatter, interacting with normal matter only in rare and violent collisions? If double-nucleus galaxies give us a way to study these extreme environments, they might also give us a glimpse into a hidden part of the universe we've never seen before. Then there's another question. If double-nucleus galaxies are home to such intense gravitational forces, could they be warping space-time in ways that we haven't yet detected? Some theories suggest that extreme gravitational environments could create gravitational echoes, subtle distortions in space-time that could reveal new insights into the nature of black holes and even quantum gravity itself. Could it be that double-nucleus galaxies are natural experiments, testing the limits of physics in ways that no laboratory on Earth ever could? Could they be giving us a glimpse into how gravity behaves on the most extreme scales, and in doing so, pointing the way toward a deeper understanding of the universe? The more we study these galaxies, the more questions arise. Are they temporary structures that will eventually fade away, or are they long-lived phenomena that play a crucial role in shaping the cosmos? Are they simply relics of past collisions, or do they represent something far stranger, something that challenges the very nature of how we think galaxies should behave? And perhaps the biggest question of all, if double-nucleus galaxies exist, could there be triple-nucleus galaxies? Or even galaxies with 4 or more central black holes? If so, how would such systems evolve over time, and what strange effects might they produce? The search for answers continues, and with each new discovery, we push the boundaries of what we know about the universe. Double-nucleus galaxies are more than just cosmic curiosities. They are windows into the deepest mysteries of space, offering clues that could one day change our understanding of reality itself. As new telescopes and advanced technologies come online, we may finally get a clearer picture of what's really happening inside these strange galaxies. But until then, they remain some of the most intriguing and enigmatic objects in the cosmos, reminders that, no matter how much we learn, the universe will always have more secrets waiting to be uncovered. The deeper we dive into the mysteries of double-nucleus galaxies, the more we realize that they challenge some of the fundamental assumptions about how galaxies evolve. We've spent decades refining models of galaxy formation, but these strange systems push the limits of what we thought was possible. Are we missing something crucial about how galaxies interact, how supermassive black holes behave, or even how gravity itself operates on cosmic scales? One of the most intriguing possibilities is that some double-nucleus galaxies may not be formed through mergers at all. Instead, they could be evidence of an alternative method of galactic evolution, one where two massive structures form independently within the same gravitational framework. This would challenge our understanding of how galaxies build themselves over time. Could some regions of the universe have conditions that naturally give rise to galaxies with two massive cores instead of just one? To explore this idea, let's consider what we know about galaxy formation. The Standard Model suggests that galaxies begin as large clouds of gas that collapse under gravity, forming stars and eventually a supermassive black hole at the center. Over billions of years, galaxies grow by absorbing smaller galaxies or pulling in surrounding matter. But what if, under certain conditions, two distinct regions of high-density gas collapse at roughly the same time, each forming its own massive black hole? If these two black holes remain gravitationally bound but never fully merge, they could create a stable, long-lasting double-nucleus structure that persists for billions of years. This would mean that double-nucleus galaxies are not just relics of past mergers but could also be a fundamental type of galaxy in their own right. If that's the case, then how common are they? Could they be far more widespread than we think, but hidden from our view because of limitations in our observational techniques? The challenge with studying these galaxies is that their second nucleus is often obscured by vast amounts of dust, gas, and energetic emissions. Many of them were only discovered when astronomers used specialized imaging techniques, like infrared observations, to peer through the dense material that surrounds them. What if there are many more out there, simply waiting to be found with the right tools? This leads us to another strange possibility. What if some galaxies appear to have only one nucleus, but actually have two, hidden deep within the chaotic environment at their center? Could some galaxies that we've long assumed to be single nucleus actually be harboring a second core that we just haven't detected yet? If that's the case, then our entire understanding of galaxy classification might need to be revised. We might need to rethink how we categorize galaxies, how we study their evolution, and even how we measure their mass and gravitational influence. Could it be that a significant percentage of so-called normal galaxies actually have complex double-nucleus structures that have gone unnoticed until now? And if that's true, then what about even larger structures, galaxy clusters? We know that galaxies themselves form massive gravitationally bound groups called clusters, where thousands of galaxies interact over billions of years. If double-nucleus galaxies exist, then could there be entire clusters where multiple galaxies each contain multiple central black holes, creating vast cosmic networks of gravitational interactions that we've barely begun to understand? This could have profound implications for our understanding of dark matter. Astronomers have long known that galaxies behave as if they contain far more mass than what we can see. This has led to the widely accepted idea that an invisible form of matter, dark matter, makes up most of the universe's mass. But what if some of the gravitational anomalies we've attributed to dark matter are actually the result of unseen double-nucleus structures within galaxies? If many galaxies secretly contain two massive cores instead of one, then that could change how we calculate the distribution of mass in the universe. It could mean that some of the unexplained gravitational effects we've observed might not require dark matter at all, but could instead be the result of complex interactions between multiple supermassive black holes. And then there's the question of what happens when these double-nucleus galaxies eventually evolve. We know that black hole mergers release enormous amounts of energy in the form of gravitational waves, ripples in the fabric of spacetime predicted by Einstein's general relativity and first detected by the LIGO Observatory in 2015. If double-nucleus galaxies are more common than we thought, then they could be some of the biggest contributors to these gravitational waves, creating detectable signals that help us map out the invisible interactions happening across the cosmos. But could some of these mergers be even more extreme than we expect? There have been theoretical predictions that, under certain conditions, merging black holes could create naked singularities, regions of infinite density that defy our current understanding of physics. If double-nucleus galaxies are sites of frequent black hole mergers, then they might also be the best places to look for evidence of these strange objects. And what about the environment surrounding these galaxies? We've already discussed the possibility that double-nucleus galaxies could produce multiple high-energy jets of radiation, but could they also influence the formation of stars in ways we don't fully understand? Some observations suggest that these galaxies might have unusual patterns of star formation, with bursts of new stars appearing in unexpected locations. Could the presence of two massive cores somehow trigger or suppress the birth of stars in ways that challenge our current models of stellar evolution? And then there's the question of whether double-nucleus galaxies could be connected to some of the most extreme cosmic events we've ever observed, gamma-ray bursts. These incredibly powerful explosions, which release more energy in a few seconds than the Sun will emit in its entire lifetime, remain one of the biggest mysteries in astrophysics. Some theories suggest that they could be caused by the collision of two black holes or neutron stars. If double-nucleus galaxies are common, then could they also be prime locations for these cataclysmic events? If that's true, then studying these galaxies might not just help us understand galaxy evolution, it could help us unlock some of the deepest mysteries about the most powerful forces in the universe. But perhaps the biggest question of all is what role these galaxies might play in the ultimate fate of the universe. If double-nucleus galaxies are sites of frequent black hole mergers, then they could be driving the growth of some of the most massive black holes in existence. Could they be helping to shape the evolution of the cosmic web, the vast structure of interconnected galaxies that stretches across the entire universe? And if black holes keep merging and growing in these galaxies, could they eventually become so massive that they start to influence the large-scale structure of the cosmos itself? Could they be helping to shape the distribution of galaxies in ways we don't yet understand? The more we study double-nucleus galaxies, the more we realize that they might not just be isolated curiosities. They could be playing a fundamental role in the very architecture of the universe. And yet, despite all of these possibilities, we've barely scratched the surface. We've only observed a handful of these galaxies in detail, and there could be countless more waiting to be discovered. As new telescopes come online and our ability to peer deeper into space improves, we may finally get the answers we've been searching for. Or, just as likely, we may uncover even stranger mysteries that force us to rewrite everything we thought we knew. The deeper we explore the mysteries of double-nucleus galaxies, the more we find ourselves questioning the very nature of the universe. If these galaxies are more than just the aftermath of galactic mergers, if they represent a fundamental stage in cosmic evolution, then what else might we have overlooked? Could they be clues to a larger, more complex pattern of galactic development that we've only just begun to notice? One of the most intriguing possibilities is that these galaxies might be transitional states in the life cycle of supermassive black holes. We know that galaxies and their central black holes evolve together, but the exact details of this process remain elusive. Could double-nucleus galaxies represent an intermediate phase between a normal galaxy and an active galactic nucleus, AGN, where a supermassive black hole suddenly erupts into a quasar, blasting out vast amounts of radiation? If that's the case, then these galaxies might be the missing link between regular galaxies and the most extreme objects in the universe. They might be the key to understanding how supermassive black holes awaken, how they regulate their host galaxies, and ultimately, how they shape the evolution of the universe itself. But here's where things get even stranger. Some astronomers have speculated that double-nucleus galaxies could be more than just the result of natural processes. They could be artificial. What if the strange structures we see in these galaxies aren't just the product of gravity, but the work of an advanced extraterrestrial civilization? It's not as far-fetched as it might sound. The idea of astroengineering, the large-scale modification of celestial objects by intelligent life, has been proposed as a way to search for evidence of alien civilizations. If a highly advanced species were capable of manipulating black holes, they might create a double-nucleus galaxy as part of some grand cosmic experiment. What would be the purpose of such an endeavor? One possibility is energy extraction. A binary black hole system could, in theory, be harnessed as an immense energy source. The immense gravitational interactions between two supermassive black holes could generate vast amounts of power, potentially usable by an extremely advanced civilization. Another possibility is that these structures are artificial stabilizers, designed to control the dynamics of an entire galaxy. Some astrophysicists have suggested that galaxies with single, dominant supermassive black holes might be less stable over time. If an intelligent civilization wanted to ensure the long-term survival of their galaxy, they might create a second nucleus as a counterbalance, preventing chaotic gravitational effects that could disrupt the formation of stars or eject habitable planets into intergalactic space. And then there's the possibility that these galaxies are the remnants of civilizations that have long since vanished. What if, instead of being artificial constructs, these galaxies are actually the ruins of ancient cosmic megastructures? Could the second nucleus of some of these galaxies be the remains of Dyson spheres, massive artificial structures designed to harness the energy of stars, that have collapsed into black holes over billions of years? If that's the case, then double-nucleus galaxies might be more than just cosmic oddities. They could be the tombstones of extinct intergalactic civilizations, marking the final resting places of species that reached unimaginable levels of technological advancement before ultimately fading into the void. But if we consider this, we have to ask an even bigger question. If double-nucleus galaxies are the remnants of ancient civilizations, then where are the living ones? Shouldn't we see signs of civilizations still thriving within these galaxies? Or is it possible that whatever caused their destruction is still out there? Could there be something about these galaxies, some fundamental property of their double nuclei, that makes them inherently unstable? What if, instead of representing the peak of cosmic evolution, they are actually the precursors to some kind of cosmic catastrophe? There have been theories that suggest that if two supermassive black holes remain in a close binary orbit for too long without merging, they could enter a phase of extreme gravitational instability. This instability could, in theory, cause a runaway reaction that results in the complete destruction of the galaxy. If that's true, then double-nucleus galaxies could be doomed to self-destruct at some point in their lifespan. But what if this destruction isn't purely gravitational? What if something else is at play? Some have speculated that these galaxies could be prime locations for the emergence of exotic physics, conditions so extreme that they break the very fabric of space and time. If two supermassive black holes interact in just the right way, they might create a scenario where quantum physics and general relativity collide, generating effects we can't even begin to predict. Could this lead to the formation of something beyond even a black hole? Some theoretical models suggest that, under the right conditions, two merging black holes could create what's known as a white hole, a hypothetical object that expels matter and energy instead of absorbing it. If that's true, then double-nucleus galaxies might not just be sites of destruction, but also the birthplaces of entirely new cosmic phenomena. And then, of course, there's the possibility that we're completely wrong about everything. What if double-nucleus galaxies aren't anomalies at all, but rather the norm? What if most galaxies go through a double-nucleus phase at some point in their lifespan, and we've simply been looking at them at the wrong timescales to notice? If that's true, then the universe might be far more chaotic and dynamic than we ever imagined. It could mean that our own Milky Way will one day develop a second nucleus, fundamentally reshaping its structure in ways we can't yet comprehend. The more we study double-nucleus galaxies, the more they seem to defy explanation. Are they cosmic fossils, evidence of past interactions that shaped the galaxies we see today? Are they active powerhouses, fueling the growth of supermassive black holes and shaping the evolution of the universe? Or are they something else entirely, something we've barely begun to understand? What's certain is that these galaxies hold secrets that could change everything we think we know about space. Whether they are remnants of ancient collisions, evidence of hidden physics, or even the marks of extraterrestrial activity, they challenge our understanding of the universe at every turn. And with every new discovery, we realize just how little we actually know. The more we study double-nucleus galaxies, the more we realize how little we truly understand about the universe. Every explanation we come up with seems to open another door to deeper mysteries. What if the very foundation of our understanding of galactic formation is flawed? What if these galaxies are telling us something fundamental about how the cosmos works, something we have yet to grasp? One of the biggest questions surrounding double-nucleus galaxies is their eventual fate. If two supermassive black holes exist within the same galaxy, does it mean they are destined to merge? Based on our current understanding of physics, the answer should be yes. When two black holes are in close proximity, they interact through gravitational waves, slowly losing energy and spiraling toward each other over time. This process should lead to a collision, a violent event that releases an unimaginable burst of energy. But here's the strange part. Some double-nucleus galaxies appear to have maintained their dual structures for billions of years. If these black holes are supposed to merge, why haven't they done so yet? Could something be preventing the merger from happening? One possibility is the existence of a third, hidden object, perhaps another black hole or an unknown form of exotic matter, that is counteracting the gravitational pull between the two nuclei. Some scientists believe that galaxies might contain dark matter cores that exert an invisible force, keeping the two nuclei apart. If that's the case, then double-nucleus galaxies could be some of the best places to study dark matter, one of the greatest unsolved mysteries in physics. But what if dark matter isn't the answer? What if there's something even more bizarre going on? Some physicists have suggested that black holes might not always behave the way we expect them to. According to certain quantum theories, black holes could be surrounded by firewalls of high-energy particles that disrupt normal gravitational interactions. If this is true, then double-nucleus galaxies might be revealing a fundamental flaw in our understanding of black holes themselves. And then there's the question of whether all of these galaxies are even normal galaxies at all. Some researchers have proposed that a few of them might not be galaxies in the traditional sense, but something entirely different, objects that exist outside the standard rules of cosmic evolution. Could these structures be failed galaxies, ones that never fully formed into the spiraling, star-filled giants we're familiar with? If that's true, then they could provide insight into the early universe, into the chaotic, turbulent time when galaxies were just beginning to form. By studying them, we might be able to peer into the distant past, uncovering the conditions that led to the birth of the first galaxies. But here's an even stranger possibility. What if some double-nucleus galaxies aren't galaxies at all, but rather massive cosmic illusions? We've already discovered that gravitational lensing, where massive objects warp the light from distant sources, can create the appearance of duplicated structures in space. Could some of these galaxies be mirages, created by the gravitational influence of unseen objects? If that's the case, then these galaxies might not actually have two nuclei. Instead, we could be looking at the distorted reflection of a single nucleus, stretched and duplicated by a powerful gravitational lens. If this turns out to be true, then double-nucleus galaxies could serve as natural laboratories for studying the most extreme warping effects in the universe, giving us a glimpse into the fundamental nature of space and time. But even if we accept that these galaxies are real, tangible objects, we still have to explain why they exist in such diverse forms. Some of them have two distinct, separate nuclei. Others have nuclei that appear to be merging. Some have one bright nucleus and one faint nucleus, while others seem to flicker between states. This raises the possibility that what we call double-nucleus galaxies might not actually be a single category at all. Instead, we could be dealing with multiple different phenomena that just happen to look similar. Some might be the result of mergers, while others could be caused by entirely different processes we don't yet understand. And then there's the ultimate question: what does all of this mean for the future of our own galaxy? The Milky Way is on a collision course with the Andromeda Galaxy, and when they merge, it's likely that their central black holes will form a double-nucleus structure, at least temporarily. Could this mean that, billions of years from now, our own galaxy will resemble one of these mysterious systems? If so, then studying these galaxies isn't just about understanding the distant universe. It's about understanding our own future. By observing what happens to double-nucleus galaxies over time, we might be able to predict what will happen when the Milky Way undergoes its own transformation. But what if our galaxy already has a second nucleus, and we just haven't found it yet? Some astronomers have speculated that there could be an undetected black hole lurking near the center of the Milky Way, hidden among the dense clouds of gas and stars. If that's the case, then the study of double-nucleus galaxies isn't just an abstract scientific pursuit. It's a direct investigation into the hidden structure of our own home in the cosmos. As technology advances, we will likely uncover even more strange and unexpected details about these galaxies. The development of next-generation telescopes, such as the James Webb Space Telescope and future space-based observatories, will allow us to peer deeper into their structures, analyzing their components with unprecedented detail. We may finally be able to determine whether these galaxies are the result of mergers, hidden physics, or something even more bizarre. But one thing is certain: the more we learn about double-nucleus galaxies, the more they challenge our assumptions about the universe. They force us to question everything we think we know about galactic evolution, black holes, and the nature of space itself. And if history has taught us anything, it's that the universe always holds more surprises than we expect. The mysteries of double-nucleus galaxies don't just challenge our understanding of galactic formation, they may also force us to rethink the very fabric of reality itself. Every time astronomers get a clearer look at these galaxies, new questions emerge, and the answers we expect often don't align with what we observe. Are these galaxies just temporary anomalies in a vast, evolving universe, or do they hold the key to some deeper cosmic truth we haven't yet uncovered? One of the biggest puzzles surrounding double-nucleus galaxies is how they manage to remain stable over such long periods. If two supermassive black holes are locked in a gravitational dance, we'd expect them to either merge or be flung apart over time. And yet, many of these galaxies have retained their dual structures for billions of years. Could this mean that some unknown force or mechanism is at work, keeping the two nuclei in balance? Some researchers have suggested that these galaxies might be surrounded by an invisible buffer of exotic matter, possibly dark matter, that keeps their two nuclei from colliding. If this is true, then double-nucleus galaxies could be acting as natural laboratories for studying dark matter itself, giving us an unprecedented opportunity to test one of the most elusive concepts in modern physics. But what if it's not just dark matter at play? Some physicists believe that there could be hidden forces in the universe, forces that we have yet to detect. For example, there are theories suggesting that gravity itself might behave differently under extreme conditions. If double-nucleus galaxies exist in regions of space where gravitational interactions are different from what we expect, it could mean that our fundamental theories of physics need to be revised. There's also the possibility that these galaxies represent an entirely new category of cosmic objects, something we have never seen before. Could it be that we've been misinterpreting these structures all along? Maybe what we're seeing isn't the result of galaxy mergers at all, but rather the remnants of an entirely different process, one that has nothing to do with the standard life cycle of galaxies. One particularly wild theory suggests that double-nucleus galaxies might not be galaxies in the traditional sense, but rather interdimensional structures, objects that exist in multiple layers of reality at once. While this may sound like science fiction, some physicists have proposed that the universe could contain extra dimensions beyond the ones we experience. If that's the case, then these galaxies could be the first observable evidence of these hidden dimensions, revealing a new aspect of reality that we've never even considered. And then there's the question of whether double-nucleus galaxies could actually be portals to something even more extreme. Some researchers have speculated that if two black holes exist within the same galaxy, they might create a kind of cosmic bridge between different points in space-time. This idea is loosely related to the concept of wormholes, hypothetical tunnels that could connect distant parts of the universe. If double-nucleus galaxies contain black holes that interact in just the right way, they could be functioning as natural wormholes, allowing matter and energy to move between different parts of the cosmos. Of course, this is all highly speculative. But if even a fraction of these ideas turn out to be true, it would mean that double-nucleus galaxies aren't just rare cosmic oddities. They're some of the most important objects in the universe, holding the answers to some of the biggest mysteries in physics. As technology improves, astronomers are beginning to get a closer look at these galaxies than ever before. The James Webb Space Telescope, for example, has the ability to peer deep into the heart of galaxies, revealing details that were previously hidden. With this new data, we may finally be able to determine whether double-nucleus galaxies are the result of mergers, hidden physics, or something even stranger. But what if we're still missing something? What if there's another layer to this mystery that we haven't even considered yet? Some scientists believe that we might need entirely new tools, perhaps even new ways of thinking, to fully understand what's happening inside these galaxies. One of the most exciting possibilities is that double-nucleus galaxies could help us unlock the secrets of black hole mergers. When two supermassive black holes collide, they release an enormous amount of energy in the form of gravitational waves, ripples in spacetime that can be detected here on Earth. By studying double-nucleus galaxies, we might be able to predict when and where the next big black hole merger will happen, allowing us to observe one of the most powerful events in the universe in real time. But there's a catch. Some double-nucleus galaxies don't seem to behave the way we expect. Instead of merging, their black holes appear to be locked in a kind of cosmic standoff, neither getting closer nor moving apart. If this is true, then it could mean that we're missing a crucial piece of the puzzle, something that's preventing these black holes from following the standard rules of physics. Could it be that these galaxies are teaching us something new about how black holes interact? Or is there an even deeper mystery lurking beneath the surface? As we continue to study these galaxies, one thing is certain: the universe is far more complex and mysterious than we ever imagined. Double-nucleus galaxies challenge our understanding of physics, space, and time itself. And the more we learn about them, the more questions we find ourselves asking. What if our own galaxy is hiding a similar secret? Could the Milky Way contain an undiscovered second nucleus, waiting to be found? Some astronomers believe that this is entirely possible. In fact, there is already some evidence to suggest that there may be a second black hole near the center of our galaxy, one that we haven't detected yet. If this turns out to be true, then the study of double-nucleus galaxies isn't just about understanding the distant universe. It's about unlocking the hidden secrets of our own cosmic home. And if that's the case, then one of the greatest mysteries of all may not be light years away, but right in our own backyard, waiting for us to discover it. The possibility that our own Milky Way could harbor a second, hidden nucleus raises even more profound questions. If a second supermassive black hole were lurking in the shadows of our galaxy's core, how would it affect the structure and evolution of the Milky Way? Could it explain some of the strange gravitational anomalies observed in the galactic center? And if we haven't detected it yet, could there be other galaxies hiding similar secrets, right under our noses? Astronomers have long suspected that many galaxies may have undergone mergers in the distant past, possibly leaving behind remnants of a second nucleus that remain undetectable by traditional observation methods. The reason we don't always see them could be due to their orientation, their surrounding dust and gas, or even the possibility that some secondary black holes are in a dormant phase, making them nearly invisible. If we develop better ways to detect them, we might realize that double-nucleus galaxies are far more common than we previously thought. This leads us to an even deeper question: what if two supermassive black holes don't always merge? According to conventional astrophysics, when two galaxies collide, their central black holes should eventually come together and merge into one even larger black hole. However, in many cases, this doesn't seem to happen, at least not on the timescales we expect. Instead, some double-nucleus galaxies appear to be stuck in a state where their black holes remain separate for billions of years. This is where an idea known as the final parsec problem comes into play. When two black holes get close to each other, they start to lose energy by emitting gravitational waves. This should, in theory, cause them to spiral inward and merge. But in some cases, it appears that the black holes slow down and stop getting closer, as if something is preventing them from merging. This paradox has puzzled astrophysicists for decades, and double-nucleus galaxies may hold the key to solving it. One possible explanation is that the presence of surrounding stars and gas influences the motion of the black holes in ways we don't yet fully understand. If a galaxy has a dense enough star cluster at its center, it might act as a kind of buffer, preventing the black holes from getting close enough to merge. This could mean that many galaxies we once thought were normal actually contain hidden binary black holes, waiting to collide, but stuck in limbo due to complex gravitational interactions. If this is true, then studying double-nucleus galaxies could allow us to predict when and where some of the most powerful black hole mergers will occur. This is significant because when two black holes merge, they create massive gravitational waves, ripples in spacetime that can be detected by observatories like LIGO and Virgo. These waves give us a unique way to study the universe, allowing us to listen, to cosmic events that would otherwise be invisible. But what if there's something even more bizarre going on? Some theories suggest that rather than merging, some pairs of black holes could remain in a stable orbit around each other indefinitely. In this scenario, the two black holes would continue circling each other in a never-ending dance, locked in a cosmic embrace that defies our expectations. This could have fascinating implications. If two black holes remain in a long-term binary orbit, they might act as a kind of cosmic particle accelerator, flinging out jets of high-energy radiation and affecting their surrounding galaxy in ways we haven't yet considered. These jets could be responsible for some of the most extreme astrophysical phenomena we observe in the universe, such as quasars and blazars, galaxies with incredibly bright, energetic cores. And if we take this idea even further, we might start to wonder, could some double-nucleus galaxies actually contain 3 or more supermassive black holes? While this might sound unlikely, there have been hints that some galaxies contain multiple massive objects at their cores. If this turns out to be the case, then the gravitational interactions between these black holes could be even more chaotic and unpredictable, leading to effects we can't even begin to imagine. This raises another question. Could double-nucleus galaxies play a role in shaping the large-scale structure of the universe? If these galaxies contain multiple black holes, their interactions could be influencing the formation of new stars, the movement of gas, and even the development of entire galactic clusters. In other words, they might not just be rare anomalies, they could be fundamental to the way the universe evolves. And here's where things get really strange. Some physicists have speculated that black holes might not just be destructive objects, but rather, they could be gateways to new forms of matter and energy. If this is true, then double-nucleus galaxies could be harboring some of the most exotic physics in existence, regions where the laws of the universe break down in ways we've never seen before. Could these galaxies be hiding something even stranger than we ever imagined? Could they be remnants of an ancient cosmic process that predates the universe as we know it? Some scientists have proposed that our universe might not be the first one to exist, but rather part of an ongoing cycle of creation and destruction. If that's the case, then the black holes in double-nucleus galaxies might be leftovers from a previous universe, ancient singularities that survived the death of a prior cosmos. And if that's true, then what else might they be hiding? Could they contain information from a time before our universe began? Could they be acting as cosmic archives, preserving data from an era that existed before the Big Bang? It's a mind-bending idea, but one that's worth considering. After all, black holes are some of the most mysterious objects in the universe, and we still don't fully understand what happens inside them. If double-nucleus galaxies contain multiple black holes in close proximity, they could be providing us with clues about the fundamental nature of space, time, and reality itself. As telescopes become more powerful and our ability to study the universe improves, we may finally get answers to some of these questions. But for now, double-nucleus galaxies remain one of the greatest cosmic enigmas, objects that defy explanation and challenge everything we think we know about the universe. And perhaps that's the most exciting part. Because every time we think we've figured out the cosmos, we find something new that forces us to rethink everything. Double-nucleus galaxies are a reminder that the universe is still full of surprises, and the deeper we look, the more mysteries we uncover. The idea that some galaxies might contain multiple supermassive black holes rather than just one raises profound implications for our understanding of galactic evolution. If these double-nucleus galaxies are more common than we currently realize, then our entire framework for how galaxies grow and change over time may need to be rewritten. What if mergers between galaxies don't always lead to a single, unified core? What if, instead, galaxies can retain multiple central black holes for billions of years, influencing their structure in ways we haven't even begun to comprehend? One of the biggest questions in astrophysics is how galaxies transition from chaotic, collision-filled environments to the more stable, organized structures we observe today. The presence of double nuclei suggests that some galaxies may still be in a long-term transition phase, slowly working toward a final state that may never fully arrive. In some cases, the two black holes may continue to orbit each other indefinitely, while in others, They may interact in ways that disrupt the flow of stars and gas in their surrounding regions. This could explain some of the irregular and peculiar galaxies we observe in the cosmos, those that don't fit neatly into the usual categories of spiral, elliptical, or lenticular galaxies. Many of these strange galaxies exhibit unexpected distortions, odd patterns of star formation, or unusual levels of radiation at their cores. Could it be that some of these anomalies are the result of galaxies with multiple black holes locked in an intricate gravitational struggle? And what about the potential for these double-nucleus systems to create gravitational waves? We already know that when two black holes collide, they release an immense burst of energy in the form of gravitational waves, ripples that travel across the fabric of spacetime itself. These waves were first directly detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO, confirming a key prediction of Einstein's general relativity. But what if we could detect gravitational waves from galaxies that contain black holes in a slow, spiraling approach toward each other? Such detections could allow us to map out the hidden binary black holes that lurk at the centers of galaxies. By studying their gravitational wave signatures, we could determine their masses, their distances from each other, and even predict when they might finally merge. In essence, we could be witnessing the early stages of future cataclysmic events, cosmic collisions that may not happen for millions or billions of years but are already shaping the structure of their host galaxies today. Even more intriguing is the possibility that some of these double-nucleus galaxies could be home to what are known as recoiling black holes. These are black holes that have been given a powerful kick due to asymmetrical gravitational wave emission during a previous merger. Instead of settling down at the center of their galaxy, they are flung away at incredible speeds, potentially traveling thousands of light years from their original location. If this is happening within double-nucleus galaxies, then some of the secondary nuclei we observe might not even be stationary. They could be black holes on the move, leaving behind long trails of disrupted gas and newly formed stars as they travel. This could help explain some of the strange, off-center, black holes that astronomers have detected in certain galaxies, which don't align with the expected central position of a supermassive black hole. And then there's the question of what happens when two black holes merge but don't completely coalesce into one. Some theoretical models suggest that in rare cases, rather than forming a single, larger black hole, a merger could result in a temporary oscillation where the black hole rings like a bell before finally settling into a new shape. If such events occur in double-nucleus galaxies, they might be responsible for some of the unusual bursts of energy we observe coming from active galactic centers. This ties into another mystery: the role of these black hole pairs in regulating star formation. We already know that supermassive black holes play a key role in shaping their galaxies by influencing the behavior of gas and dust. A black hole can act as a sort of cosmic thermostat, regulating when and where new stars form. But if a galaxy has two or more black holes, the process becomes far more complex. The gravitational interactions between the black holes could create alternating periods of intense star formation and sudden quenching, leading to the bizarre and varied appearances of galaxies we see in deep space surveys. And what if some of these double-nucleus galaxies are actually the precursors to something even stranger? Galaxies that will eventually become entirely dominated by black holes. In the distant future, some astronomers predict that the ultimate fate of many galaxies will be to become black hole galaxies, where the majority of their mass is locked away inside supermassive black holes, with only a sparse halo of stars remaining. If that's the case, then the galaxies we see today with double nuclei could be glimpses into this far-off destiny. They could represent a middle stage in an evolutionary process where galaxies are slowly being consumed from the inside out by their own central black holes. Over billions of years, they might transition into a state where almost all of their visible matter is gone, leaving behind only the immense gravitational wells of the black holes themselves. But there's also another possibility, one that challenges our entire view of black holes as inescapable voids of destruction. Some radical theories suggest that black holes might not be the final stage of collapse, but rather doorways to something else entirely. If so, then double-nucleus galaxies might be more than just sites of galactic mergers. They could be cosmic laboratories where new physics is taking place, revealing secrets about the very nature of space, time, and even parallel universes. For instance, some theories propose that when black holes merge, they don't just produce gravitational waves. They might also generate exotic particles or even tiny, temporary gateways to other regions of the universe. If any evidence of this is found within double-nucleus galaxies, it would completely transform our understanding of reality itself. And if we take this idea to its ultimate conclusion, we might ask, what if double-nucleus galaxies are actually points where our universe is interacting with something beyond our comprehension? Could they be sites where the fabric of space-time is unusually thin, allowing glimpses into dimensions beyond the three we experience? At the moment, these ideas remain speculative, but the fact that double-nucleus galaxies exist at all is proof that the universe is still full of surprises. Every time we think we understand how galaxies work, we find an exception, something that doesn't fit the pattern, something that forces us to rethink our assumptions. As we continue to study these galaxies with ever more advanced telescopes, we may uncover even stranger phenomena lurking within them. Perhaps we'll find entire populations of galaxies with multiple nuclei, suggesting that our current theories of galaxy formation are incomplete. Or maybe we'll detect unusual energy signatures that hint at processes we've never encountered before. One thing is certain, the deeper we look into the universe, the more mysteries we uncover. Double-nucleus galaxies are not just peculiar cosmic oddities. They are windows into a deeper, more complex reality, one that we are only just beginning to understand. And the most exciting part? We've barely scratched the surface. The idea that we may be observing galaxies in the middle of a long, drawn-out transformation challenges the very way we categorize and understand them. Traditionally, astronomers have classified galaxies based on their structure: spiral, elliptical, lenticular, and irregular. But double-nucleus galaxies force us to consider an entirely new dimension of classification: the evolutionary stage of a galaxy's core. What if many of the galaxies we see today are simply snapshots of a much longer and more complex process? Some galaxies might be in the early stages of merging, with their dual nuclei still relatively distant from each other. Others might have already merged in the past but left behind remnants, gravitational echoes of an older structure that we can still detect. And then there are the ones in between, where the two nuclei are close enough to influence each other gravitationally but not yet fully unified. These galaxies may exhibit strange behavior, with stars and gas moving in unpredictable ways, as if caught in a cosmic tug-of-war between two supermassive black holes. One of the most fascinating aspects of this phenomenon is the way it challenges our assumptions about galactic stability. We often imagine galaxies as relatively stable structures, slowly evolving over billions of years. But if double-nucleus galaxies are common, it suggests that many galaxies are in a constant state of flux, their very centers shifting and reshaping over time. This could have profound implications for our understanding of dark matter as well. Dark matter is one of the greatest mysteries of modern astrophysics. It is invisible, yet it exerts gravitational influence on galaxies, preventing them from flying apart despite their rapid rotation. If double-nucleus galaxies are more common than we realize, it could mean that dark matter plays an unexpected role in their evolution. Perhaps the presence of multiple black holes influences how dark matter is distributed within a galaxy, altering the way stars and gas behave on a large scale. And what about the impact of these dual black holes on their surrounding environments? We know that black holes can launch powerful jets of high-energy particles into space, shaping entire galaxies in the process. But what happens when two black holes are present, each with its own accretion disk and jet? Could they create interference patterns in the surrounding gas, leading to chaotic bursts of star formation? Could they interact in ways that generate shockwaves, altering the chemistry of interstellar clouds? Some observations suggest that double-nucleus galaxies may indeed be responsible for some of the most energetic and extreme phenomena in the universe. Certain quasars, galaxies with extremely bright, active cores powered by feeding black holes, may actually be double-nucleus systems in disguise. If so, it would mean that some of the most luminous objects in the universe owe their brightness to the gravitational dance of two massive black holes, each contributing to the release of immense amounts of energy. And this leads to another intriguing question. Could some of these double-nucleus galaxies be precursors to the formation of even more exotic objects, such as binary supermassive black holes? If so, they could serve as laboratories for understanding the final fate of black holes in a universe dominated by mergers and collisions. As our telescopes become more powerful and our computational models more refined, we may soon be able to answer some of these questions. The upcoming James Webb Space Telescope and future observatories will allow us to peer deeper into space, uncovering more double-nucleus galaxies and analyzing them in unprecedented detail. Perhaps we will find that they are far more common than we ever suspected, forcing us to rethink how galaxies grow, evolve, and ultimately fade away. One thing is certain: the more we learn about double-nucleus galaxies, the more we realize how little we truly understand about the universe. These strange, complex systems challenge our theories and push the boundaries of what we thought was possible. They remind us that the cosmos is not a static, predictable place, but a dynamic, ever-changing environment where the unexpected is the norm. And perhaps, just perhaps, they hold the key to some of the most profound mysteries of existence itself. The discovery of galaxies with double nuclei raises fundamental questions about the long-term fate of galaxies and the nature of their central black holes. If two supermassive black holes exist within the same galaxy, what happens when they finally merge? The answer could reshape our understanding of gravitational waves, cosmic evolution, and the very structure of space-time itself. One of the most exciting possibilities is that these double-nucleus galaxies are breeding grounds for gravitational wave events. When two supermassive black holes spiral toward each other, they send ripples through the fabric of space-time, disturbances so powerful that they can be detected across the universe. The first detection of gravitational waves in 2015 confirmed that black holes can collide, but those were relatively small black holes, only dozens of times the mass of the Sun. Now, imagine two supermassive black holes, each millions or even billions of times the mass of the Sun, locked in a final death spiral. The gravitational waves produced by such an event would be unlike anything we've ever observed, shaking the very foundation of physics. Scientists believe that these colossal mergers could release energy equivalent to billions of supernovae exploding at once. The sheer power of such an event would briefly outshine entire galaxies, sending shockwaves of radiation across the cosmos. And if we could detect these signals, they would provide an unprecedented opportunity to study black hole physics, test Einstein's theory of relativity under extreme conditions, and perhaps even uncover new laws of nature. But before these mergers happen, galaxies with double nuclei exist in a strange in-between state. Their twin black holes interact with each other, and with their surroundings in complex ways. Some double-nucleus galaxies appear to be in a period of relative calm, with the two black holes still orbiting far apart. Others show signs of chaotic activity, with stars caught in unpredictable orbits and gas clouds twisting under the influence of competing gravitational forces. This suggests that there is no single path to merger. Some black holes may take billions of years to collide, while others may be on the verge of merging right now. One of the big mysteries surrounding these systems is how they affect the rest of the galaxy. We know that a single supermassive black hole can regulate star formation, acting almost like a thermostat. If a black hole is feeding aggressively, it can generate winds and radiation strong enough to blow away gas, shutting down star formation entirely. But what happens when there are two? Could they create alternating cycles of intense star formation and sudden suppression? Could their competing gravitational forces stretch and tear apart molecular clouds, leading to bursts of star formation in unexpected regions? Observations suggest that double-nucleus galaxies often display irregular star formation patterns, with regions of young, hot stars mixed alongside areas of old, dying ones. This chaotic distribution hints that the presence of two black holes may be disrupting the usual process of stellar evolution, creating pockets of activity where stars should have burned out long ago. Another mystery involves the movement of stars within these galaxies. In a normal galaxy, stars tend to orbit in relatively stable paths around a single central mass. But in a double-nucleus system, those stable paths are disrupted. Some stars might be caught in orbits that change unpredictably, swinging between the influence of one black hole and then the other. Others might be flung out entirely, ejected from the galaxy at extreme speeds. These so-called hypervelocity stars have been observed racing through intergalactic space, and some astronomers believe that double-nucleus galaxies may be responsible for launching them. And then there's the question of whether all double-nucleus galaxies eventually merge. Some may never complete the process. If a galaxy has a particularly high amount of dark matter, for example, it could prevent the two black holes from getting close enough to merge, leaving them locked in an eternal gravitational dance. Others may have their merger process disrupted by an external force, such as another passing galaxy that disturbs the delicate balance. This raises a deeper, more philosophical question: are galaxies permanent structures, or are they just temporary arrangements of matter in an ever-changing universe? If double-nucleus galaxies are a sign of constant transformation, then it suggests that no galaxy is truly stable. Instead, every galaxy may be a fleeting, transient structure, slowly evolving into something new over billions of years. The study of double-nucleus galaxies isn't just about understanding how galaxies merge, it's about understanding the very nature of cosmic evolution. It challenges our assumptions about stability and permanence, forcing us to see the universe as a place of constant motion and transformation. It reminds us that even the largest structures we see in the night sky are not fixed, but instead caught in an endless cycle of creation, destruction, and rebirth. And the more we learn, the more questions we uncover. Are there galaxies with triple nuclei? What happens if two galaxies with double nuclei merge? Could that create a system with 4 black holes? If black holes grow faster in these systems, could double-nucleus galaxies be the key to understanding the mysterious quasars that shine at the edge of the observable universe? The future of space exploration may hold the answers. With upcoming observatories like the Laser Interferometer Space Antenna, LISA, we will be able to detect gravitational waves from merging supermassive black holes for the first time. That means we won't just be seeing double-nucleus galaxies, we'll be listening to them. We'll be able to hear the faint tremors of black holes colliding, like cosmic drumbeats echoing through the universe. And as we continue to explore, we may find that double-nucleus galaxies are not just a rare curiosity, but a fundamental part of the story of the cosmos. They may be the missing link between the galaxies of the past and the galaxies of the future. They may be windows into a deeper, hidden order that we have yet to fully understand. The mystery is far from solved, but one thing is certain: galaxies with double nuclei are more than just an astronomical oddity. They are a glimpse into the raw, untamed forces that shape the universe. And as we peer deeper into space, we are only just beginning to unravel the secrets they hold. The implications of galaxies with double nuclei stretch far beyond the question of black hole mergers. These systems might also provide critical insights into the formation of galaxies themselves. The standard model of galaxy evolution suggests that galaxies grow over time through mergers, absorbing smaller galaxies and accumulating mass. If this is true, then double-nucleus galaxies could represent an intermediate stage in this process, a brief but critical moment in which two separate galactic cores are in the process of fusing into one. But what determines whether two galactic nuclei merge completely or remain separate for billions of years? The answer may depend on several key factors, including the presence of dark matter, the amount of interstellar gas, and the complex gravitational interactions within the system. In some cases, the two nuclei may spiral inward relatively quickly, their mutual gravitational pull drawing them together in a few million years. In others, they may enter a more stable orbit, remaining as twin cores locked in an endless celestial dance. One of the biggest obstacles to merging is the phenomenon known as dynamical friction. When two supermassive black holes orbit each other, they interact with the surrounding stars and gas, losing energy in the process. Over time, this should cause them to spiral closer together. But in some galaxies, this process appears to stall, leaving the two black holes separated by thousands of light years for incredibly long periods. This is known as the final parsec problem, and it remains one of the unsolved mysteries in astrophysics. One possible solution is that interactions with gas clouds and star clusters help to bridge the final gap, allowing the black holes to continue merging. Another possibility is that external factors, such as gravitational waves or the influence of a third black hole, are needed to complete the process. If this is true, then some double-nucleus galaxies could be waiting for an external disturbance to trigger the final collapse. Interestingly, some double-nucleus galaxies appear to contain black holes that are actively feeding on surrounding material. When a black hole accretes matter, it emits powerful jets of radiation and high-energy particles. If two supermassive black holes in the same galaxy are both feeding at the same time, this could create a unique signature: two sources of intense radiation coming from different locations within the same galaxy. Observing these dual-active galactic nuclei could provide clues about how black holes grow and interact with their surroundings. Some astronomers have even speculated that these double-nucleus systems could be responsible for some of the most energetic phenomena in the universe, such as quasars. Quasars are extremely bright objects powered by the rapid consumption of matter by supermassive black holes. If a galaxy contains two actively feeding black holes, the combined energy output could be even more extreme, potentially explaining why some quasars are among the most luminous objects ever observed. There is also the question of what happens to the stars and planets that exist within these galaxies. If two galactic nuclei are merging, the gravitational forces involved can disrupt entire solar systems, sending stars careening into interstellar space or causing them to collide with each other. Some planets may be torn from their orbits and flung into deep space, becoming rogue planets wandering the cosmos. Others may be drawn into the gravitational influence of one of the black holes, spiraling inward until they are eventually consumed. For any civilization that might exist within such a galaxy, the effects would be catastrophic. Entire regions of space could become uninhabitable as radiation levels rise and gravitational disturbances wreak havoc on planetary systems. If intelligent life exists in one of these galaxies, they may witness their sky being reshaped in real time, with the two galactic cores growing brighter as they move closer together. And then there is the ultimate question: what happens when two supermassive black holes finally merge? The event would unleash an enormous burst of gravitational waves, distorting space-time itself. If the merger happens within our cosmic neighborhood, the shockwave could be powerful enough to briefly alter the orbits of planets, though the effects would likely be too small to notice. But on a larger scale, the energy released could shape the structure of the surrounding galaxy, triggering waves of star formation or even altering the trajectory of other nearby galaxies. The study of galaxies with double nuclei is not just about understanding mergers, it's about unraveling the deeper mechanics of the universe. These systems challenge our understanding of gravity, black hole physics, and the evolution of galaxies. They hint at hidden processes that have shaped the cosmos for billions of years, processes we are only beginning to comprehend. And yet, despite all we've learned, the biggest mysteries remain. How common are these systems? Are they a rare phenomenon, or are they just a brief but inevitable stage in the life cycle of all galaxies? Could some galaxies contain even more than two nuclei, with multiple black holes locked in a chaotic dance? Could there be hidden galaxies where mergers are happening right now, their signals just waiting to be detected? With new telescopes and observational techniques, we are getting closer to answering these questions. Instruments like the James Webb Space Telescope and the upcoming gravitational wave detectors will allow us to peer deeper into space than ever before, revealing the hidden dynamics of these enigmatic systems. One day, we may witness a double-nucleus galaxy in its final moments, capturing the precise instant when two black holes merge into one. But until then, the mystery remains. Galaxies with double nuclei are a reminder that the universe is still full of surprises, that even the largest structures in the cosmos are not as stable as they seem. They are proof that space is not static, but constantly shifting, evolving, and reshaping itself in ways we are only beginning to understand. And as we continue to explore, we are certain to uncover even more secrets hidden in the vastness of the universe. Galaxies with double nuclei are more than just cosmic anomalies. They are windows into some of the most powerful and mysterious forces in the universe. The presence of two galactic cores suggests not only a past merger but also a potential future catastrophe. But beyond the sheer gravitational spectacle of these systems, They may also hold clues about how galaxies evolve, how black holes grow, and how some of the most energetic events in the universe unfold. One of the most fascinating aspects of double-nucleus galaxies is the way they challenge our assumptions about galactic stability. For a long time, astronomers assumed that galaxies were relatively settled structures, slowly evolving over billions of years through star formation and gradual gravitational interactions. But the discovery of multiple galactic cores suggests that chaos is far more common than we once thought. If two galactic nuclei can remain separate within the same galaxy, it raises a critical question: how many galaxies might actually contain multiple cores that we simply haven't detected yet? Some astronomers believe that hidden double-nucleus systems could be lurking in many of the galaxies we have already catalogued. The challenge is that, from our perspective, these secondary nuclei may be obscured by dust, gas, or even the bright light of the main core. In some cases, the two nuclei may be so close together that distinguishing them is nearly impossible with current observational technology. Future telescopes equipped with more advanced infrared imaging and gravitational wave detectors may help us uncover these hidden systems. And then there's the question of what role dark matter plays in these systems. Dark matter is one of the biggest mysteries in astrophysics, an invisible substance that doesn't emit or reflect light but exerts gravitational influence on galaxies. Some researchers have proposed that dark matter could help explain why some galaxies maintain separate nuclei for so long. If a double-nucleus galaxy has a significant dark matter halo, this could create a stabilizing effect that prevents the two cores from merging quickly. In this scenario, dark matter acts like a cosmic buffer, keeping the galactic cores apart for millions or even billions of years. Another mystery surrounding these galaxies is the fate of the stars and planets trapped between the two cores. When two supermassive black holes orbit each other, their combined gravitational pull can create intense tidal forces that disrupt the orbits of nearby objects. Some stars may be ejected entirely from the galaxy, becoming rogue stars that drift through intergalactic space. Others may be drawn into elongated orbits that take them dangerously close to one of the black holes. And for those unfortunate enough to cross the event horizon, their fate is sealed. They will be stretched and torn apart by the black hole's immense gravitational forces in a process known as spaghettification. But what about entire solar systems? Could a planet survive in a galaxy with two galactic nuclei? Theoretically, a planet in the outer regions of such a galaxy might remain in a stable orbit, relatively unaffected by the gravitational tug-of-war between the two black holes. However, the closer a solar system is to the galactic center, the greater the disruption. A planet in an unstable orbit might experience dramatic shifts in climate and radiation exposure as it moves through regions of varying gravitational influence. If intelligent life were to evolve on such a planet, it would face an unpredictable and chaotic cosmic environment, one where the night sky might shift dramatically over the course of millennia, as entire star systems are displaced. Some researchers have even speculated that double-nucleus galaxies could be prime locations for studying high-energy astrophysical phenomena. The gravitational interactions between two supermassive black holes could generate powerful jets of plasma, gamma-ray bursts, and even exotic forms of matter that are rarely observed elsewhere in the universe. If we can study these galaxies in greater detail, we may be able to unlock new insights into the physics of extreme environments. Insights that could one day help us understand the nature of black holes, gravitational waves, and even the fundamental structure of space-time itself. One of the most exciting possibilities in the study of double-nucleus galaxies is the potential to observe an actual black hole merger. Scientists predict that when two supermassive black holes finally collide, the resulting energy release will be one of the most powerful events in the universe, sending ripples through space-time in the form of gravitational waves. These waves have already been detected on smaller scales by observatories like LIGO and Virgo, but a merger between two supermassive black holes would be orders of magnitude more powerful, an event so extreme that it could reshape entire regions of space. Detecting such an event would not only confirm many of our theories about black hole physics, but it could also provide new insights into how these mergers influence the evolution of galaxies. Some astronomers suspect that the shockwaves from a black hole collision could trigger star formation on a galactic scale, igniting bursts of new stellar activity in the surrounding regions. Others believe that these mergers could be responsible for some of the most energetic cosmic phenomena we observe, including certain types of quasars and active galactic nuclei. But perhaps the most intriguing question of all is whether double-nucleus galaxies are a glimpse into our own galaxy's future. The Milky Way is on a collision course with the Andromeda Galaxy, a massive spiral galaxy located about 2.5 million light-years away. Astronomers predict that in about 4.5 billion years, the two galaxies will begin to merge, creating a new, larger galaxy sometimes referred to as Milkomeda. During this process, the supermassive black holes at the centers of both galaxies will eventually interact, potentially forming a double-nucleus system similar to the ones we observe today. If this happens, our galaxy may undergo a period of instability, with stars and solar systems being displaced or even ejected into deep space. The final fate of our solar system in this scenario is uncertain. Some models suggest that the Sun and its planets might remain relatively undisturbed in the outer regions of the merged galaxy. Others indicate that the gravitational chaos could push our solar system into a completely different orbit, or even fling it out of the galaxy entirely. And if humanity, or any form of intelligent life, still exists at that time, they may witness one of the most dramatic cosmic events imaginable, the birth of a new galactic core, forged from the remnants of two ancient ones. As we continue to study these enigmatic galaxies, we are reminded that the universe is far from static. Galaxies are not fixed islands of stars, but dynamic, evolving structures shaped by immense forces over billions of years. The discovery of galaxies with double nuclei challenges our understanding of cosmic evolution and forces us to rethink the way galaxies form, grow, and ultimately die. Each new observation brings us closer to answering some of the most profound questions in astrophysics. Questions about the nature of gravity, the fate of black holes, and the hidden forces that govern the cosmos. And yet, despite all that we have learned, these galaxies remain full of mysteries. How many more double-nucleus galaxies are waiting to be discovered? What unseen forces influence their evolution? And what will we learn when we finally witness one of these systems reaching its ultimate fate? The answers to these questions may redefine our understanding of the universe itself. As we delve deeper into the mysteries of galaxies with double nuclei, one question looms large: how do these systems form in the first place? While it might seem logical to assume that every double-nucleus galaxy results from a past galactic merger, the reality is far more complex. Some of these galaxies appear to have formed their dual cores through completely different processes, ones that challenge our current understanding of galaxy evolution. One possibility is that some double-nucleus galaxies began as single-core galaxies but later developed a second nucleus due to internal dynamics. This could happen if a massive cloud of gas and dust collapses in the central region of a galaxy, forming a secondary concentration of stars and possibly even a smaller black hole. If this secondary structure remains stable for long enough, it could function as a second nucleus, even without an external galactic collision. Another theory suggests that some double-nucleus galaxies might not actually contain two supermassive black holes at all. Instead, what we see as a second nucleus could be a dense cluster of stars or a particularly bright region of star formation that mimics the appearance of a galactic core. If this is the case, then these galaxies may not be as chaotic as they seem, at least, not in the way we originally thought. But what about the galaxies that do contain two supermassive black holes? The dynamics of such a system are incredibly complex. When two black holes orbit each other at the center of a galaxy, they create a unique gravitational environment. This can lead to a phenomenon known as dynamical friction, where the gravitational influence of nearby stars and gas gradually slows the movement of the black holes, causing them to spiral closer together over time. However, this process can take millions or even billions of years, meaning that many double-nucleus galaxies we observe today may be in a temporary state, one that will eventually resolve itself when the two black holes finally merge. The merging of two supermassive black holes is one of the most violent events in the universe. When it happens, an enormous amount of energy is released in the form of gravitational waves, ripples in the fabric of space-time itself. These waves travel across the cosmos, carrying with them the signature of the black hole collision. Scientists hope that by studying galaxies with double nuclei, we can one day predict when and where these collisions will occur, allowing us to observe them in real time. But what if some double-nucleus galaxies never merge? There is a possibility that certain galaxies contain black holes that will remain in a stable orbit around each other indefinitely. This could happen if the two black holes are surrounded by enough dark matter or if they interact in such a way that their momentum keeps them from ever colliding. In such cases, these galaxies could exist in a state of equilibrium for billions of years, with two distinct cores coexisting in the same galactic structure. The idea that some double-nucleus galaxies might persist indefinitely raises another fascinating question. Could this be a stage in a longer cosmic cycle? If two black holes in a double-nucleus galaxy never merge, they might instead interact with surrounding matter in ways that influence future star formation, altering the evolutionary path of the galaxy. This could mean that some galaxies go through repeated cycles of forming, disrupting, and reforming double nuclei over vast cosmic timescales. And then there's the question of how these systems affect the distribution of matter on a galactic scale. The gravitational interactions between two central black holes can create turbulence throughout the entire galaxy, potentially affecting everything from star formation to the movement of interstellar gas. In some cases, these interactions might lead to the formation of galactic rings, elongated stellar structures, or even entire regions of space that are unusually devoid of stars. If we can understand the full impact of double-nucleus galaxies on their surroundings, we might be able to uncover deeper insights into the large-scale structure of the universe. But perhaps the most mind-boggling possibility is that double-nucleus galaxies could be connected to an even greater mystery: the nature of dark energy. Dark energy is the unknown force that appears to be driving the accelerated expansion of the universe. While we still don't fully understand how it works, some scientists speculate that interactions between massive objects, such as supermassive black holes and double-nucleus galaxies, might provide indirect clues about its effects. If we can measure how these galaxies evolve over time, we might be able to detect subtle hints of dark energy's influence on their dynamics. Ultimately, the study of galaxies with double nuclei is not just about understanding a rare cosmic phenomenon, it's about unlocking fundamental truths about the universe itself. These galaxies represent a unique and chaotic state in the grand cosmic dance, a moment where forces of unimaginable power are at play. Each one is a laboratory of extreme physics, offering us a glimpse into processes that shape not just individual galaxies, but the very fabric of space-time. And yet, for all that we have learned, the questions continue to multiply. How many of these galaxies exist beyond our observational reach? Could some of them hold entirely new forms of matter or unknown physical interactions? And what will happen when we finally witness the most dramatic stage of their evolution, the moment when two galactic cores collide, unleashing a burst of energy that echoes across the cosmos? The mysteries of these galaxies remind us that the universe is still full of surprises. Even as our technology improves and our understanding deepens, there will always be cosmic riddles waiting to be solved. And perhaps, somewhere out there, among the countless galaxies scattered across the universe, the next great discovery is already unfolding, just waiting for us to find it. The search for galaxies with double nuclei is not just about observing a rare phenomenon, it's about understanding the larger picture of how galaxies form, evolve, and sometimes even die. Every time we find a new one, we are essentially peering into a unique chapter of cosmic history, one that could hold the key to unraveling some of the deepest questions about the universe. But as we look deeper, new questions emerge, and some of them challenge our very perception of what we think we know about space. For instance, could galaxies with double nuclei be more common than we realize? Most of our observations are limited by the power of our telescopes, and many distant galaxies appear as mere blurs of light. What if a significant percentage of these blurred images actually contain two separate cores, but we just don't have the resolution to see them clearly? If that were the case, our entire model of galactic evolution might need to be revised. To push this theory further, astronomers have turned to advanced techniques such as gravitational lensing, where the light from distant galaxies is magnified by the gravitational pull of massive objects in the foreground. This allows us to see details we wouldn't normally be able to detect. With better instruments and deeper observations, we may one day realize that double-nucleus galaxies are not an anomaly, but a fundamental stage in the life cycle of many galaxies. Another mystery that surrounds these galaxies is how they interact with their surroundings. When two supermassive black holes exist within the same galaxy, their immense gravitational pull can cause extreme disruptions in the movement of nearby stars, gas, and dust. This can lead to the creation of elongated stellar streams, unusual orbital paths, and in some cases, massive outflows of material that shoot out into intergalactic space. These outflows, known as galactic winds, are thought to play a critical role in regulating star formation. Some scientists believe that galaxies with double nuclei could be some of the most extreme examples of galactic winds in action. If two black holes are locked in a close orbit, their combined gravitational energy might be enough to drive powerful jets of matter outward, expelling gas and dust at speeds approaching the speed of light. This could have significant consequences for the future of the galaxy, potentially stripping it of the very materials needed to form new stars. But what if the opposite is true? What if, instead of destroying star-forming material, these galaxies are actually responsible for creating new stars at an accelerated rate? Some observations suggest that regions around double nuclei contain large amounts of dense gas, which could collapse under its own gravity to form new stars. If this is the case, then rather than being destructive, double-nucleus galaxies could actually be some of the most productive star factories in the universe. And then, of course, there's the question of what happens when two black holes in a double-nucleus galaxy finally collide. This event would be one of the most violent occurrences in the universe, releasing more energy in a fraction of a second than our Sun will emit over its entire lifetime. The collision would send ripples through space-time in the form of gravitational waves, which we could detect using sensitive instruments like the LIGO and Virgo observatories. The detection of gravitational waves from a merging pair of supermassive black holes would be groundbreaking, confirming yet another prediction of Einstein's general theory of relativity. But it could also tell us something even more profound: how black holes grow over cosmic time. If double-nucleus galaxies are a common stage in galaxy evolution, then their mergers might be the primary way that the largest black holes in the universe come to exist. And what about the possibility that some of these mergers never complete? Some theoretical models suggest that in certain cases, two black holes might enter into a stall phase, where they orbit each other for billions of years without ever merging. This could happen if there isn't enough gas, stars, or dark matter around them to help carry away their orbital energy. If this is true, then the universe could be filled with countless binary black holes locked in an endless dance, waiting for the right conditions to finally bring them together. The more we study these galaxies, the stranger the questions become. Could some double-nucleus galaxies be the remnants of ancient cosmic collisions, where entire galaxies once merged but never fully settled into a single core? Could some of these systems contain wormholes, hypothetical bridges through spacetime that could connect distant regions of the universe? While wormholes remain speculative, the extreme gravitational conditions of double-nucleus galaxies make them an interesting place to look for new physics. And then there's the ultimate question: are we seeing these galaxies at a particular moment in their life cycle, or are some of them stable structures that will persist indefinitely? If the latter is true, then we may need to rethink our definition of what a galaxy even is. Perhaps some galaxies exist in a perpetual dual-core state, maintaining two central masses without ever merging into one. The truth is, we are still in the early stages of understanding galaxies with double nuclei. Every new discovery brings more questions than answers, and the more we learn, the more we realize how much we still don't know. But that's what makes space so exciting. It's not just about finding answers, it's about expanding the limits of what we thought was possible. And somewhere out there, in the depths of the universe, another galaxy with two bright, mysterious cores is waiting to be discovered. The only question is, what will it teach us next? This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.